Visible, right? So I'll
Yeah,
stop.
it's full screen. Yeah, it's full screen now, so it's okay. So maybe I think we should start now. Uh, we need to be on schedule today because from 2 p.m. we have something else, the panelist also. So let me welcome all the panel members, our distinguished speakers, and the members of the organizing committee, and also warm welcome to all the attendees who have taken their time to join the day 5 of this 5-day online uh, faculty development program on computational chemistry, in chemistry and material science, or computational techniques rather say. So I welcome you all in the first session of day 5. We have Dr. Monojit Bag today with the lecture session 6. So um, I think he's already he has been introduced previously, and we all have heard the beautiful lecture from him before. So without wasting much time, and I would request Dr. Bag to kindly deliver your talk, please.
Okay, thank you, Dr. Ghosh and Dr. Bag for inviting me and all this organizing team. So also, I also wanted to start my presentation without wasting much time because this is a field I feel like this is quite upcoming and a lot of challenges are there. So I think a lot of things can be discussed, but I don't know how much I can cover within a 1 year. I mean, sorry, 1 hour. I mean, like this is a few years of work. So in 1 hour, I don't know how much I can compress. So I'll try my best to just touch upon few aspect of the issues and challenges in this area people are working on. So the talk is iron migration in perovskite. This is quite challenging in the sense uh, when people started working on perovskite solar cell, people thought, okay, this is really wonder materials and we can do a lot of things. But the device degrades in sunlight. So it's like a piece doesn't like water. I mean, that is the kind of situation you can think about. Like, then what can happen? So that's what everybody's started looking into how it can be improved. So we'll show some experimental evidence of ion migration. Then there are some theory how these migration pathways are, and maybe some ion kinetics at the end. So before going into my full presentation, I would like to introduce my group activities right now at Arise Lab we are doing. So there are three major areas currently I'm looking at. One is perovskite light emitting diode. Basically, these perovskite materials are quite good for light emission. So you can look for white light or display technologies where perovskite can be used. Second is photo electrochemistry. So these materials can also be useful for hydrogen evaluation. Basically, like you can split water using photoelectrochemistry, and then you can use that as later on. The third is the large area perovskite device. Definitely, like when we talk about the perovskite solar cell, it has to be large, right? It cannot be like small area. You need to generate a lot of energy. So these are the three major areas I'm looking at. Definitely, there will be a lot of collaboration needed to understand the device physics from the theoretical perspective as well. So just to give you a brief introduction, like this, as probably last lecture, Dr. Chakravarti has already mentioned, it is actually evolved from dye-sensitized solar cell. So that's sort of like you can call it like parents. Dye-sensitized solar cell is the parent for uh, perovskite solar cell. So if you look at the device structure here, so you have a basically, sorry, I need to use laser pointer. So you have a counter electrode, the working electrode, which is nothing but nanostructure TiO2, then coated with dye. Then you have a counter electrode, and then you have electrolyte. So whatever the chemistry happening here, so dye basically gets excited, gives electron to the TiO2, and then TiO2 gets transported to the anode electrode here, and then you have oxidation reduction happening at the electrolyte interface, and then uh, this gives the electron this hole this side. So then you complete this complete circle, you get like a solar cells, right? So that is the typical dye-synthesized solar cell structure. Now, in 2009, there is a group from Japan. Uh, they thought, okay, why not uh, this organometal halide can be used as dye? So they thought of like, okay, put TiO2, then use this perovskite as a dye, and then they fabricated the dye-synthesized solar cell. But it was only like 3.7% maximum efficiency they achieve with iodide based MAPBI3 basically. That is the dye they have used. They have also used MAPBR3, but that efficiency is lower. So this work was almost unnoticed till 2012 when Smith group from Imperial College, they published a science paper with more than 12% efficiency in perovskite, and that caught the attention of everybody. Okay, this could be really breakthrough. So then there are a lot of noise about perovskites. You can see in 2013 he published one JPCL. It's a perspective basically. So what he told, like the result took us. So in this study, what they observed is if you use alumina oxide rather than say TiO2. TiO2 is the electron conductor, whereas alumina is not. It's an insulator. So if you use alumina like a insulator and then use perovskite as your dye, then you get even higher efficiency and higher voltage. They achieve like almost like 200 to 300 millivolt higher voltage for alumina. So then they thought, like, okay, these perovskites not only act as a dye, but it also transport charges. So that is kind of a breakthrough. So they said like, oh, there is a new era, new avenue of research and development for the low-cost solar cell, which has been emerged on the perovskite semiconductors. So that is sort of like breakthrough in this field. And then the lot of people started interested working in perovskites in various ways, and you can see the device architecture also evolved with time. So initially there used to be like very thick TiO2 layer, then you have the dye electrolyte, liquid electrolyte, and counter electrode that started shrinking, and finally we end up with only perovskites and compact TiO2 and electron transporter and hole transporter like this. So you can see the how the device structure has changed over a period of time, and the efficiency also has gone up from 3.7% to now more than 25% in a decade or so. Right. So now if you compare with the contemporary technologies, like what people are using, their material cost, their raw material, fabrication cost, energy payback period, efficiency and stability, and if you compare with say cadmium telluride, CIGS, or crystalline silicon and perovskites, you see all other technology may have some difficulties in somewhere. Either their cost is high, or their fabrication is high, or maybe some efficiency is not so high, and so on. So they are not all green. But if you look at the perovskite column here, the material cost really low, finished material also low, fabrication cost because it's solution processable, it's also low. Energy payback, definitely if all costs are low, payback period will be very fast. Efficiency, it's really high. Now the biggest question comes here, where we are. So start with red. I would say that's what I put some sort of like shaded color here. So, or sort of like you can say like the rainbow color here. So start with somewhere like red, but definitely we are going towards green. So definitely if you can make this completely green, this could be the materials which we are looking for quite a long time. So what are the promise? You can see like they are very high efficiency, over 20%. Their cost is low, they are solution process, but definitely there are a lot of obstacles. Like these materials are not very reproducible in the sense you can make say 5 millimeter by 5 millimeter or 1 centimeter by 1 centimeter device, but as you go on increasing the device size, the efficiency goes down. It also has lead content, but again, this is, I don't know whether this should be a big concern or not, because a lot of materials we use, even like the solder we use, that has lead. But if you can encapsulate properly, probably we can take care of the uh, exposure to the environment. But there will be again question, like when there is a breakdown, what will happen to the materials? We cannot just dispose to environment, right? So there has to have some sort of a policy to take care of that. The third is the stability under sunlight, and that is the biggest concern. Like these devices are not stable under sunlight, and that is what we started thinking. What could be the reason why these materials are so unstable? So in early 2014, I got interested to work in this field because one of my collaborator from University of Loyal, they actually started fast, in fact. So they came to our lab, and then they were saying that, oh, we make this device, we make like 7 to 8% device quite easily, but within an hour or so, it degrades to like 1%, or maybe it doesn't even work at all. So that actually caught our attention, and why it is degrading. So that is the beginning of this project. Definitely, there are a lot of advantages, as I said. Maybe some of the band gap tuning part I'll come at later on, like how theoretically we can predict what could be the band gap. So definitely you can change the cationic sides, anionic sides, and the lead to the combination of lead and tin. You can make wide band gap to even very small band gap. Although the stability wise, some of them would be good, some of them may not be that good, or the what you call this optoelectronic properties also can vary depending on the materials we choose. But the bottom line is you can tune the band gap in these materials quite easily just by mixing two different materials. So there are different fabrication procedure. Definitely over a period of time, this process has been optimized, and people are able to make very good quality film, because these are semi-crystalline or nanocrystalline film. So depending on how you process, you can get really good crystals, right? So there are two major approaches, I would say. One is solution process deposition. Other one is vapor deposition. Vapor deposition. Solution process, again, you can think about a single step precursor deposition method where you mix two components like lead iodide and methyl ammonium iodide, or maybe like lead halide and methyl ammonium halide, or maybe instead of methyl ammonium you can take like formamidinium, you can take cesium iodide or cesium halide. So you take all these precursor, dissolve into DMF or DMSO, or mixture of DMF DMSO, and then just spin coat onto a substrate and then annihilate. So you will get a very smooth film. But early days, actually, people did not get very good quality film with this method. So then they moved to sequential deposition, where you deposit lead iodide first, and then you introduce the second layer of, say, methyl ammonium, either by spin coating or dip coating, or maybe the thermal sublimation method. So then you can get good quality deposition. So this is another method I was talking about. This vapor based deposition, where you can have two source. One is your lead iodide, other one is methyl ammonium iodide. You can have substrate. You can co-deposit like this, or you can have, again, sequential method. You deposit lead iodide first, and then you can introduce methyl ammonium vapor, such that this methyl ammonium can basically infuse into the lead iodide matrix and form the three-dimensional perovskite structure. So these are different methodologies. A lot of engineering has gone into it. So you can add a lot of additives. You can do a lot of process condition to get much better film qualities. Okay, in 2014, actually, there was a paper from Yang Group. They reported 19%, although this was not NREL certified, they reported 19%. But there was one data hidden in the paper that was in the supporting information, not even a main paper. So they measured the efficiency in ambient air, dry atmosphere, and nitrogen atmosphere. So you can see, even if you put in a nitrogen atmosphere, it's not very stable over like hours. You can see like within 140 hours, this efficiency from like whatever the maximum efficiency, it goes down to like 20%, right? So you start with 20% device, it goes to like only 4% or so on. So that is the challenge in this field, and that's what we also got interested to look at how this device degrades, or why this device degrades. Later on in Kamath group also, they published a paper in JAX where they said, like, if you expose this perovskite to moisture under light, so they call it like excited state, uh, uh, transmission of excited state photovoltaic efficiency. So under humidity and light, these materials actually convert into some sort of like hydrated compound, where these materials lose the color, so it doesn't absorb in visible range anymore, and you lose the device efficiency. Then in early 2015, there was another paper by this Cards group. They showed that you can have bromide-based perovskites, and you can have halide iodide-based perovskites. Apparently, bromide-based perovskites are slightly stable over the iodide base. So if you start with iodide base MAPV3 and you expose it to 100 sun, that's really high intensity of light and heat, so it degrades to lead iodide. Whereas if you start with MAPVBr3, it is relatively stable compared to this material. So all these experiments, keeping in mind, actually we started working on this project where we make very simple structure. This is actually inverted structure for perovskite, and maybe like you can call it normal structure for organic solar cell. So start with or rather I would say like this is a PIN structure. So you have ITO P.PSS as whole transporter, you have active layer, your perovskites, then you have the electron transporter PCBM, and then you can either deposit calcium aluminum or lithium fluoride aluminum. So we have started with calcium aluminum. Everything has to be within inside glove box, otherwise device will not be stable at all. And we got not so high, but at that time it was quite comparable efficiency with reported literature. Like early 2014, like around 14-15% was sort of like typical efficiency in the solar cell device, perovskite device, and that is the efficiency we got at that time. Later on, we have optimized; we have got more than 20% now. So now the interesting observation is when you expose your solar cell to light, the device gradually degrades. So these are exposed. And then this black one is basically like when you keep this device under dark condition for some time, you can see there is a little bit of reversibility. Although this is not 100%, this is I would call like sort of quasi-reversible process. So if you keep this device under dark for some time, you can regain some of the efficiency, and that definitely like over a period of time it degrades. But as you keep on keeping it in dark condition, it can regain some of the efficiency here. So, and then what we did is we did EIS measurement, electrochemical impedance spectroscopy, for each device at different point. And what we noticed is, so I'll not go to the very details of the EIS setup and experimental technique. What we understood from the EIS is what is the carrier lifetime, what is the, if there is any ion migration, we can basically calculate the diffusion coefficient and conductivity and so on. So here you can see these are typical EIS data under dark. This is under light, and you clearly see under dark you don't see multiple semicircles. You just see one semicircles. But as you go to the light IV curve, you can see there is a semicircle followed by another one, and the second one is basically the reason behind the ion migration. Just to compare with the organic solar cell, if you look at the organic solar cell, you never see this kind of behavior. I mean, you don't see this second semicircle at all. This is under dark, this is under light. You always see one semicircle. So that is the reason, and that is the puzzle actually started thinking, what is that, the second semicircle? And there are a lot of reports about the low frequency components. So people thought of like it could be due to the charge accumulation. Later on we thought, okay, it's not only charge, it could be ion accumulation at the interface. So there are different, like people started looking at different interface and see like how this second semicircle behaves. So there are a lot of models to explain the second semicircle, and maybe I'll come to this point here. So some interesting observation here, the second semicircle is not always the same. So if you look at the different device, you can see the and sometimes it looks like purely a semicircle. Sometimes it looks like there is some sort of a straight line followed by a curved uh, uh, impedance. So if this is a semicircle, we can say like this is because of the charge accumulation. If there is some sort of a straight line, this is because of some carriers are migrating. So that's sort of like diffusive behavior. And because now we understood these perovskites are a mixed conductor, so basically you have the electronic conduction as well as ionic conduction. You can see this double layer to the Warburg component, right? So that's the biggest difference, and that is what we also struggled to publish this paper, because early 2015 nobody was able to believe these big ions can migrate through this perovskite structure. A lot of argument went on, and then finally like community believed that okay, it is the ion migration. So we started the different model, and finally end up with this model where we have the Warburg component, which gives the quantitative analysis for ion migration. And also we checked with the impedance versus square root of omega, 1 over square root of omega plot. If this two gives the straight line in this plot, this is related to the ion migration. The slope gives the Warburg impedance, and the intersection gives the charge transfer resistance here. So that is the typical model, and then we do the basically different bias voltage dependent, and you can see like how this parameters changes, how the high frequency semicircle changes, how the low frequency semicircle changes, and you can clearly tell that this high frequency component is basically coming because of the electrons, and to some extent it could be very fast ion, like maybe like iodine or bromide. Whereas this low component is because of the ion which is there, like this cation, bulky cation. It could be methyl ammonium, it could be formamidinium, it could be even like lead can migrate, but it may have higher activation energy barriers and so on. Right? And we can fit with this equation, this Warburg equation, and this P defines what nature of Warburg. It could be like semi-infinite, it could be finite diffusion model. So there are different, depending on what kind of diffusion it is, this P component can vary. So then we thought like, if it is related to the migration of ion, why not to try a bulky ion which can sort of reduce the migration? And that's what we started thinking about this formamidinium. And that time, not many people were, familiar with this counter ion, basically this Fa. And somehow we were able to make the efficient device with mixture of Ma and Fa. This one was not that optimized. Later on, people have got even higher efficiency with FAPBI3, but that time we are not able to achieve very high. But just for the comparison, we have kept it here, and you can see there the AFM morphology. How these are all nanocrystalline materials. We have done some grazing incident, wide angle X-ray scattering to see the crystallinity, and you can see in some cases you do see some lead component, lead iodide component, and these peaks are the 100 perovskite peak, very prominent peak. So what we noticed is, if you keep these three devices like MAPBI3, FAPBI3, or the mixture of this, these two, to some extent, they are stable. Whereas MAPBI3 degrades even inside glove box, and this is in days, so you can see like the degrades even inside glove box. Whereas these two doesn't degrade that much under dark condition, but definitely it can degrade under light. So also, like when you go to the mixed halide, or mixed cation, the hysteresis also gets reduced because of reduced migration. I'll come to that point later on. So we started looking at the migration kinetics using temperature dependent studies. And what we noticed is, if you look at this migration, this has really low activation energy barrier when it crosses some sort of a threshold temperature around 320 Kelvin. So that's around like 53 degree centigrade, 40 to 50 degrees centigrade, right? 53. So MAPBI3 actually degrades quite fast after you increase the temperature beyond certain temperature. And then we notice that there is a phase transition for MAPBI3 around 55 degrees centigrade. So if you increase the temperature beyond that, it goes to tetragonal phase to cubic phase, and then MAPBI3 degrades even much faster. So these are some degradation study. You can see we have used LED, which doesn't have the infrared component to heat up the sample. We use the solar simulator, which is basically uh, quite similar to like sunlight, but it has the IR and UV component both. And if you look at it, under solar simulator, actually this MAPBI3 degrades, but if you expose it to LED light, it doesn't degrade that much, right? Solar simulator, both these device degrades, but under LED light, it doesn't degrade that much. So that means under heat, it degrades even faster. So that also we check with the XRD data. So this is heating at around 45 degrees centigrade. This is at room temperature. You can see there is a shift in peak position, which gives indication that there is a change in crystal volume. So you can see it here. So these are all different structure of MAPBI3, APPBI3, and MAPBI3. These are all cell parameters. And if you look at the this spacing, this one actually increases quite drastically compared to the other two devices. So MAPBI3 actually expand more than the mixed halide or APPBI3 based device, and that could be the reason why this device degrades. So this is one schematic you can see when the device is under heat but without light, you can cool it back. So this peak will be like heating, it will shift this way, and cooling, it will come back. So you don't see the degradation here. But if you apply heat and light both, what will happen is this peak will disappear, and then this lead iodide peak will basically reappear again. So what happened is this tetragonal or cubic phase of lead iodide, MAPBI3, gets converted into lead iodide, and this is a two-dimensional structure. And then methyl ammonium iodide actually gets removed from the structure itself. So that is the reason when you have heat and light, this device degrades so fast. So we have also done some control experiment. You can see like this is heat, no light. This is heat with LED light, and this is a solar simulator. So with no light, it doesn't degrade much, so only 5% drop. But if you have heat and white LED, that's quite similar to like solar simulator, so it degrades even more. And under solar simulator, you can see this is also degrade like 23% after 17 hours of exposure. This is a continuous exposure, by the way. So bottom line is, if you have solar simulators or sunlight, so it has two components. One is your visible component, which is essential for your energy conversion, but at the same time you have infrared, which basically heats up your sample. It doesn't contribute to the light or device efficiency, but it heats up your sample, and that is the reason for degradation. So we also checked with, like, if you take a KG5 filter, which cuts down the infrared, then the device efficiency can be improved. So this is one example you can see with this KG5 filter. So with the solar simulator and KG5 filter, the device actually, this stability is improved. This is all MAPBI3 samples. So this is sort of schematic. This is not exactly what is happening. But what happens is when you have the thermal expansion, this lattice actually expand. And then if you have light, this MA plus, basically methyl ammonium counter ion, actually escape from this three-dimensional cage. And that is the reason for degradation. And finally, it got published in JAX, but after a lot of argument, it was in Nature Chemistry for quite long time under review for, but then that time, as I said, like probably this work was quite ahead of time, and people are not able to believe, oh, there is an ion migration. Later on, we have got a lot of papers in ion migration, theoretically as well as experimentally. So that is the challenge. So as I said, this warper is basically the reason for all this degradation and so on, right? Okay, why my slides is okay? Now it's fine. I think there is some issue. Sorry, I think my slide is just going its own way. Okay, fine. Okay, then when I moved to Sweden, actually, there is a group who does work on single molecule spectroscopy, but as I said, like everybody has strategy about perovskites, and they also started working with perovskites, and they used to do all this super resolution microspectroscopy. So then we started working in a project where we have a very tiny crystals and we expose it to light and see the emission spectrum over a period of time. And what we noticed is, as the device degrades or whatever the reason, the emission spectrum shifts towards the blue emission. You can see this is the spectrum when we start, and then this spectrum slowly shifts towards the blue emission like this. So here is one video. You can see. Let me see if this video can be played. Maybe not. There's some issue with that. So otherwise you could see this is the first order image, this is the actual image, and this is the first order diffraction, and you could see this spectrum actually shifts. Somehow this video is not working in my this laptop, probably in other laptop is to work. So what we understood is when we expose this device first, you see this red emission. This is the microscopic image, right? And after sometimes you can start seeing this part actually becomes greenish, like this red emission disappears and you start to see the greenish. So then we started looking at these two sample under ACM. So this is the real sample, and that is after degradation. So you can see these are not actually the crystalline sample. These are sort of hydrated samples. And if you look at the XRD pattern, it will be something similar to like lead iodide. And that is what, when you expose a nanocrystalline sample, it degrades to lead iodide. So that is what we propose, some sort of a schematic here. So you start with three-dimensional MAPBI3. So you have all these counter ions, you have nice structures. This angle is somewhere around 170 degree for MAPBI3, this iodine lead iodine structure, and you get emission somewhere in 770 nanometers. Now, as this ions start migrating out, am I audible? Audible, right?
Yes, Manoj,
Yeah.
you are audible. Yes.
Yes.
As the ions start migrating out, you can see, because there is a void space, what will happen is all this octahedral, they try to minimize the energy and they try to collapse basically, right? So you can see these bonds actually start to decrease, and if more and more ion migrates out, this whole structure will collapse into two-dimensional lead iodide structure. And from the experiment, from the theoretical calculation, we can show that when the angle is maximum, like 180 degree, you have the minimum band gap, and that's what you get the emission around 770 degree, 770 nanometers. But as it goes to two-dimensional lead iodide, this bond angle comes to somewhere 120, and the emission spectrum becomes somewhere around 500 or 510 nanometers, somewhere like that. So that means if you look at the emission spectrum of any materials, perovskite materials under illumination, you can see how the structure gets collapsed from 3D to 2D halide structures, right? So then comes to some theoretical aspect of it. You can see there is a paper from Philip Group published in Nature Communication 2014. What they propose it, there are iodide, there are halide, and there are all these counter ions. So you can see the energy landscape of all these halide, lead, and counter ions, and you can clearly see only iodine 5p and to some extent lead 6s contribute to the HOMO level, or the you can say like the top of the valence band, right? Now, if you look at the bottom of the conduction band, it is basically the lead 6p and to some extent iodine 5p. So it's mostly lead 6p. So if you look at any transition, it will be iodine 5p to lead 6p. So that is the transition. So in this structure, this cation doesn't contribute to the band structure directly. The cationic contribution is somewhere here, right? So they don't contribute to the band structure explicitly, or the band gap I don't say like band gap explicitly, but what it does is when you change the counter ion from methyl ammonium to some other counter ion, this bond angle changes, and that play a big role in contributing to the band gap here. So this is another example. You can see they have used lot of different cations, and you can use the Goldsmith-Lawrence factor where it could be like whether it will form like a nice cubic structure or it would be tilted structure. Depending on that, you can tune your equatorial bond angle from 120 to 180 depending on what counter ion you use, and you can tune your band gap from say 1.1 to 1.9 or maybe like 2.3 depending on what structure you are looking at. So you can have wide band gap tunability, as I said, like depending on what counter ion you choose and so on. So this is one example like how the steric size and bond angle varies, as well as like when you change the bond angle or the band gap varies. So these are some of the typical materials that are used to calculate the band gap starting from say 0.99 to like 1.79. So this was published in Nature Communication in 2014 by this group, right? So then there is another paper from, this is actually De Angelis group. So De Angelis actually does lot of ion migration study by theoretical calculation. So they use some sort of a DFT and modified DFT method to see how these ions migrate. So normally iodine can migrate through either through void space as well as the interstitial, because this is a very small, whereas methyl ammonium counter ion only can migrate through void. So if you have a crystals with lot of ion vacancies, they are very prone to ion migrations. And lead can also migrate, but definitely the activation energy barrier is much higher, order of like 1 eV, whereas methyl ammonium or iodine has a activation energy barrier somewhere like 0.1 or less than 0.1 eV, so they can easily migrate. Methyl ammonium could be somewhere like 0.5 to 0.8 depending on like different group report, different calculation and so on, but they are mobile than much more mobile than lead, right? So these are all like deformation, energy formation, like how the defective energy forms at different state. You can see like lead vacancies, iodine interstitial. This is iodine vacancies and where it can be, and what are the energy landscape for different degree vacancies and so on. And the bottom line is you can predict how the carriers are migrating or what is the defect energy formation. Definitely, like when you expose it to light and heat, you basically giving that much of energy to the systems, and it can create a lot of defects. At the same time, it can also annihilate defects. So there are some example where people have observed activated what do you call this, photo activated defect healing, basically like your photoluminescence increases when you expose it to light. So in that sense, like some of the defect state gets annealed or healed because of the thermal activation and light activation. So that is also there. So there is a kinetic process. So it's not always that the defects are fixed. So they are always migrating, and it can create, it can again annihilate. So then coming back to our group work again, in 2018, we saw that this defect ion migration not only contribute to the stability issues, but it also contributes to the electronic transport. So we cannot decouple ion and electron from this perovskite material. So both are very strongly correlated species. So charge and ion both are strongly correlated species. And as you go on increasing the bias voltage, you do see different features at different point of time. So this is one schematic. You can see how this net field flipped its polarity. So because you have a built-in potential, you have photogenerated potential. Along with that, you have a potential due to the separation of ions at the respective electrode side. So all three voltage actually interdependent. So when you apply a little bit of voltage, this ions start to migrate, and the field due to the ion that actually reduced. And you can see there is an inflection point, and the net voltage again start to increase. So That's what you can see the anomalous behavior in perovskite materials when you do voltage dependent transport measurement. So it doesn't always like monotonic function. So coming back to the degradation again, from the EIS data, we have extracted a lot of parameters. And if you look at the device efficiency versus Warburg impedance, so higher the Warburg impedance, lower the ion migration, by the way. So when we have very efficient device, this Warburg impedance is high, so the ion doesn't migrate much. But as the ions start to migrate, there are a lot of voids created within the sample, and then what do you call this migration become even faster and faster. So you can see the impedance becomes smaller and smaller as you go on lower and lower efficiency. It has a lot of defects, and these ions start to migrate. And also they start to accumulate at the interface. So why I'm saying that? Because if you look at the flatband potential, as the device degrades, the flatband potential increases, and that reflects that lot of ions are actually accumulated at the hole and electron transport interfaces, and that creates problem to extract efficient charges from the respective electrode. So device degrades means we are not able to extract charges from both sides quite easily. So this is another example how this ion gets complete with the picture with the electronic properties. So this is a quite recent publication. It was one of the most read paper from August, in the month of August. This is applied materials. Here what we have shown that if you have a very smooth surface, these ions actually start pile up at the interfaces. This is the bromide ion, this is the methyl ammonium iodide, methyl ammonium counter ion. So if these ions are basically stuck at the interface, they form sort of a dipole which changes the band offset here and prevent the further charge injection. So the efficiency actually decreases here. Now if you somehow make this interface rough or sort of like this structure, what will happen is this correlation is sort of lost because all these ions are at different places. All these dipoles are not very well aligned, and then the strong dipole moment is sort of broken here. So it flattens out the band, and you can easily inject carrier from this side, and you can have in fact high efficiency number. Not only that, this also contribute to some sort of a anomalous behavior which is quite new in this perovskite materials. You see negative capacitance. So when you measure capacitance, you generally don't expect the capacitance should be negative. That means when you apply voltage, it should store charge rather than like this negative capacitance means it is sort of inductive effect, you can call, right? Then storing charges, it generates more charges there. So or leakage, more charges there. So you can see also like when you change the interface from smooth to texture, they have a different behavior in this the negative capacitance. But bottom line is, in both cases you do see negative capacitance because of this ions are accumulated at this interface. So this is another quite new experience for us. Also, we have never seen this before in perovskite materials. Perovskites are also like ambipolar in the sense it can conduct electron and hole quite easily. Mobility wise, they are quite comparable. And you can tune the properties by changing the interface, right? If you apply positive bias or you choose only hole transport materials, it can behave like a p-type materials. Or if you choose only electron transport materials, it can behave like a n-type materials. This paper actually have demonstrated that it can have p-type behavior and n-type behavior on the same geometry by just doing some interface engineering. And all this ion in fact contributes to the overall device performance. You can see how these ions are piled up at the interfaces. Apart from this electrolyte side, definitely electrolyte is purely ionic conductors. You don't have the electronic conductors, but the perovskite also has the ionic conduction, and that can be influenced by this ion as well. So you can see how this ionic contribution play a big role in the impedance spectrum. So, and also if you look at the absorption, this is the field induced absorption. You can see two absorption peak, which is quite similar to like the photo-induced bleaching band, like photo-induced bleaching band 1 and 2. This is what we call like field-induced bleaching band, which are comparable to this photo-induced bleaching band due to this two valence band theory. Right? You can see in this perovskite you have two different valence band. That's how you have a emission or absorption spectra at higher energy side as well as lower energy side, and you can populate or depopulate depending on how do you extract charges at different places, and you can do a lot of photophysical studies using this geometry as well. So I would say like I will not go to much details about it, just to summarize, and maybe we'll discuss more into it. So just to summarize, so there is always a photo-induced ion migration, and that is one of the key problem in perovskite solar cell. So somehow we have to prevent that. So and the mechanism we have already shown. So some of the strategies we can say, like you can change the halide ions, you can change the cationic side. Recently we are working on that. So basically we use multi-cations and multi-halide perovskite. So it's called like MCMS, mixed cation mixed halide perovskite. So there you can improve the stability by changing both, right? And if you can reduce the operating temperature, the device efficiency can be improved. And definitely, like when you use outside, you cannot reduce the temperature, but lot of recent studies shows that these materials could be really good for indoor light recycling. So for example, like if you put your photovoltaic device inside your room, it can collect your room light and generate a lot of energy. So that is called indoor photon recycling. So this is also upcoming technologies or upcoming ideas, rather than technology I'd say, like this upcoming ideas, people are doing that. That is like these ions also responsible for negative capacitance. This is quite new in perovskite materials. This is there in other materials also, like normally organic LEDs, you might see this negative capacitance, but perovskite is quite new. Then coming back to the band structure, as I said, the cation doesn't contribute to the band structure explicitly, but it determines the lead halide bond angle and hence alters the band gap. So depending on what is the Goldsmith tolerance factor, you can increase the cationic sides. It will not only give you the stable perovskite, but it will also reduce the band gap, right? And the electronic charge transfer is not decoupled with ion, so there is always a correlation. So recently I have submitted a couple of papers where we have shown that this coupling in fact gives rise to some sort of a superlinear power law behavior in the AC conductivity. So that probably under review right now. So I have not discussed that, but these are the effects in perovskites. So with this, I'd like to thank my collaborators and group. I have been working. This is quite similar to the earlier presentation I've given, but here you can see like Professor Ivan Siblikin, where I've done this super resolution microspectroscopy, decouplers group, some device fabrications, and some analysis in negative capacitance. And these are the that time PhD students work with me with this project, and some PhD students currently working with me in this perovskites project. With this, I would like to thank, and I'll be happy if there is any questions and queries.
Thank you, Dr. Bag, for your enlightening lecture on the perovskite materials that are upcoming fields of research in the interface of chemistry and material science indeed. So thank you very much. And I would request the participant, if you have any queries or questions for discussions or to know, please put your question in the Q&A box. So it will help us to find your question and answer them. So. Or we otherwise we can take the question in the discussion session as well. We had that one.
That is fine. So yeah, because as I said, like this is quite diverse area of research, so it's very difficult to compress in single lectures. But I tried to cover different aspects of like ion migrations, like how they can impact device efficiency, stabilities, and other areas. So probably it was quite concise. So I hope like
Manojit.
yes.
Yeah, may I ask something?
Yes, sure, sure.
Yeah, yeah. So first of all, it's really a nice talk. I really enjoyed thoroughly. I have one query. I mean, can you comment on this? I think the ion migration people are trying to see for the hysteresis effect, right? I mean,
Yes,
in the peroxide material.
yes,
And
yes,
there also a kind of initiative from theoretical understanding, mostly from this Filippo Angelis group and then
yes, yes. This Angeles group actually,
Andrew
they
Rapin
do.
group. They are trying to say this ferroelectric nature. So,
Yes.
I mean, what's your take on that? I mean, does it really affect the hysteresis, or is
Uh,
it mostly the ion migration?
I see. Personally, I believe it is ion migration. I have not done the theoretical part yet, because when you talk about ferroelectricity, probably yes for say MAPBI3.
Mm-hmm.
So because MA has a really large dipole moment,
Mm-hmm.
but if you move to say cesium or say Fa, you don't see too much of dipole moment. Now the question is, the ferroelectricity will come when you have the little bit of distorted crystal structure. You cannot get it in like purely cubic structure probably.
Yeah.
So in
Yeah.
room temperature, yes,
Mm-hmm.
but there is still some argument whether this is really ferroelectric properties. There are
Exactly.
paper, I know, right? There are some
So, but
paper
from
also.
experimental side, people have seen ferroelectricity in
We
this kind
have
of
not
material.
seen many paper on experimental side. Probably there is a recent paper from Ungsman Nag's group. Probably or there is another group from ISA Pune. I forgot that group, either Ungsman Nag or somebody else.
Ogle.
They recently I've seen one paper. They have tried different perovskites, and they studied some dielectric properties and ferroelectric properties. But
Acha, yeah,
apparently
I got
yes,
that. Yeah, I think it's
they have
Ogle
shown there is
is
a PE
there.
loop.
Mm-hmm.
They have shown there is a PE loop. Yes.
Mm-hmm. Mm-hmm. Mm-hmm.
So, but though it's not very high PE loop, like unlike like ferromagnetic, you can clearly see these, or some ferroelectric material you can clearly see the square shape PE loop.
Mm-hmm.
But they have some PE loop. I remember vaguely.
Mm-hmm.
So I have not done that, but yes, people are looking at ferroelectric properties
But it's mostly
and trying to
prevailing
correlate with the hysteresis.
due to the iron migration, you think? I mean, I
I
also
still
think.
believe it is the ion migration, because it is quite understandable that ion migration is quite easy, and
Yeah,
ion can just get stuck at the interface,
yeah,
right, at
yeah,
the defect
yeah,
sites, and
yeah.
that has been proven.
Okay, okay.
So probably that has more, or it could be both. I mean, I'm not denying that it's there is no ferroelectric effect. It could be
Mhm.
both, right?
Okay,
The
okay.
ferroelectric, basically we are looking at the dipole, only the dipole contribution, where ion
True.
migration is ion is physically moving. So
Yeah.
they are in fact correlated, right?
Yeah. I mean, if you have like random ion, I mean, this organic cation rotation, that might
Yes,
give you the dipole moment. Okay, excellent.
yes.
I
So
just
if
want
the
to have
interface
the
this
experimental
yes.
take on that. Yeah. Okay.
So probably the temperature dependent study will help to some extent. But again, when you do the temperature dependent study, migration also will be reduced, right?
Exactly.
So
Yeah.
it is very difficult to decouple this ion migration contribution to the ferroelectric.
True.
We can prove
True.
there is a ferroelectric effect. We can prove there is ion migration. But which
Mm-hmm.
one exactly contributing to the hysteresis? It's very difficult.
Mm-hmm.
Nowadays, in fact,
Mm-hmm.
people are reporting hysteresis free perovskite for large area, or what you call large crystals perovskites. People are able to make millimeter size crystals, and they are saying that there is no hysteresis.
Which
So I
group?
believe,
Do you know?
I think Mahito's group, Aditya
Mm-hmm.
Mahito's group, you can see
Uh-huh. Okay.
they have
Uh-huh.
a few science paper,
Okay.
and they are able to make like millimeter size large crystals,
Uh-huh. Uh-huh.
and they
Okay.
are saying that there is no hysteresis. So there is a science paper from Mahito's group long time back, maybe like 2015 or 16 sometimes.
Okay.
Uh,
Okay. Good.
they have
Good.
showed that there is. See, my point is, if you are somehow able to make really good quality perovskite film without less defects, I would expect neither it will have hysteresis nor it will have ion
Exactly.
migration.
Yeah. Yeah.
Right.
Yeah.
So theoretically, you can also study that. Like if you
Mm.
create a structure without defect, probably your activation energy barrier will be quite high. Only iodine can migrate. Iodine can still migrate through the interstitial, so you cannot avoid the iodine migration.
Mm.
But that
Mm.
is not the only reason to degrade, right?
Mm. Mm.
So they
Mm.
are always mobile, and that is quite fast.
Okay.
Whereas methyl ammonium, or the what do you call this cationic migration, is the reason for degradation.
Mm-hmm. Mm-hmm.
right?
Yeah, I think, yeah, I mean, we can discuss more in the discussion session probably.
Yes,
It's
yes,
a really
yes.
nice point, actually. Thank you. Yeah.
I think, Dr.
Uh,
Bag, we have one question from Santanab Giri. It's instead of methylamine, if we can use bulky amine, can ion migration be reduced?
yes, to some extent it should reduce, but again the question is whether it will form a stable perovskite or not. So there is, as I said, if you look at this Nature communication paper I have cited, so you can see how the tolerance factor also changes. So it is very difficult to introduce very bulky counter ion within the case like this framework, right? So from methyl ammonium to permamidinium to guadinium, to some extent, guadinium even bulkier than the permamidinium. But how much amount you can introduce? Now, if you introduce a mixture of triple cation, so there are a lot of reported triple cation perovskites which are more stable. But again, it will depend on how much you can introduce. So we cannot just make very bulky counter ion. It will not make basically a 3D structure. So there are a lot of 2D perovskites. I have not touched upon that. But in recent years, people are basically looking at 3D, 2D interface, where 2D perovskites are more stable than 3D. Because 2D perovskite, you don't have that much of ion migration. Although there may be like iodine migration, but not the counter ion migration. So people are looking at 2D, 3D interface where you can have, or you can arrest the ion migration and improve the efficiency. Yes, I mean like bulky, I mean can reduce the ion migration, but question is whether device the perovskite will be stable or not at that tolerance factor. Right. There will be any other question? No, I guess.
So I think so far we don't have. And so I would like to thank Dr. Bag once again, and very good interaction with Dr. Chakraborty indeed. And we will have more of that sort in our discussion session, I believe.
Yes, sure.
And thank you very much for sharing your the data and sharing your work, research work on this. I would not say upcoming. This is already on the surface. The
Yeah.
perovskite, they have got a lot of attention. So
Yeah, I mean,
150,
like I
yes,
don't know how many groups in the world is working for
yeah,
skites.
I think
So
more than hundreds groups are
no, more than
working
1,000, I would
definitely.
say. More than
1,000,
100 is
yes,
too less.
yes.
So maybe within India, you can say like 100
Yeah,
people are
hundreds
working.
groups. Yeah, exactly. So this has already upcome the groups, the research. So thank you very much once again, and I think we will have you in the discussion session when
Yes,
we
sure.
start at around 12, after 12. So thank you very much. Thank you.
Thank you. Thank you. Thanks a lot.
So we have our second session, that should be the hands-on session. So we just had our the last lecture session by Dr. Bag, and now we will have our last hands-on session on the day 5 of this 5-day online FDP, and that will be delivered by Dr. Sumantra Bhattacharya from NIT Sikkim, and he will be delivering on the topic of Gaussian IRC, TD density functional theory, and studying reaction mechanism. So with this brief introduction, may I request Dr. Bhattacharya to kindly share your screen and just deliver your talk. Please, sir.
Thanks a lot. I'm here. IRC, before starting IRC, I should start a bit backward, that is on the transition state theory. Not theoretical, I'm not going to transition state theoretical details. Details can be found in several books like Chemical Kinetics by Laidler and some other books on the potential energy surface. These books details clearly discuss on that. But the thing is that one few basic things I should say, the transition state is a point in a whole potential energy surface. Some cases, some research studies show that during transition state, nothing take place. Whatever the bond breaking formation and bond making formation will take place before, just before and after the transition state. and these calculations can be shown by using the local mode analysis. What is the local mode analysis? Local mode analysis is a special kind of vibrational mode analysis where, suppose, let us take this structure. Let us optimize the structure of what a methane I have. If I calculate the structure of normal modes of vibration, I'll see that a particular vibrational mode will not consider only just two atoms. Instead, it will consider a group of atoms which is known as the normal mode of vibration. Like here, you see, by using the displacement vector, three molecules are rotated. But such kind of the local modes of vibration cannot be shown here. But in that case, suppose let us consider the vibration between 1 and 4, then in that case, all the other atoms except 4 and 1 are considered to be inside 1, and 1 is having infinite mass. That means only 4 will move up. Rest of the things will be fixed. In this way, I can get particular mode only, change in particular systems, but not the whole. Is this visible now?
Sorry, your screen is not visible.
Dr. Bhattacharya, it's not shared.
No, sir, it is not visible.
Oh, I have not
Kindly
shared
reshare,
screen.
sir.
Sorry. I'm extremely
Yes, sir.
sorry.
Yeah, it's coming now.
It's coming now, right?
Yeah.
Suppose I have methane molecule, and for the methane molecule, I study the vibration. These normal modes of vibration for a particular vibration, what I have seen, let us take the vibrational mode 1 and start the animation along with the displacement vector. I will see the displacement vector will go in a particular direction, and this will involve number of atoms, right? Thus, this type of motion is normal modes of vibration which include particular atoms of the system. But instead, if we take the local mode of vibration, let me stop here. Local mode of vibration, in that case 1 and 4, let us take the vibration between 1 and 4. I have to include 2, 5, 3 into 1, and 1, 4 should be considered with the fact that 1 and 4, among 1 and 4 have the infinite mass is concentrated only on 1, not on the 4, right? Hence, only I'll get one information. Using this, it is seen that some bonds are breaking just before the transition state, and after the transition state some bonds are forming, and in this course I am just getting a maxima for that point. Now for the practical purpose, how can we calculate the transition state? Let us take a simplest system. It is the substitution reaction, SN2 substitution reaction, where the chloride atom is substituted by the bromide atom. How to do this? The simplest process is to calculate. To do this, the first step will be attacked by the bromide atom, thus forming a transition state, and at the transition state they will form a 5-member pentavalent carbon atom sorry, and this carbon atom will be formed like structured this way. But the thing is that choice of this transition state is not that easy. As we have told yesterday, last day class, that this transition states, finding transition state structure is more of practice and arts than a science. As you have seen that we have find this structure where chlorine, bromine and carbon, chlorine, carbon and bromine are forming 180 degree, and these carbons are almost making a equilateral triangle. How to calculate? The calculation shows that we have to do the op plus frequency, and we are giving Ts Bernie. We should use the force constant ones. Method as usual I have made that ground state Hartree-Fock default spin, and I have not changed the basis set. It is 631 G. But what will be the charge? Charge will be -1 because chloride atom because attack of bromide atom ion will come up, not bromine atom. Hence the overall charge of the system will be -1, and thus making this spin state of the system as a singlet. Here as usual I made TS, and rest of the things I didn't change. Submitting the job will give us the output file, which I have already done. Hence I am not showing the calculational detail. Let us see what will be the calculational detail. Our structure has been formed. You have seen that we have made the force constant frequency will be found at the after optimization the structure, right? Thus in the whole process I can see their structural detail. Can you make out that these structures how they are changing? Chlorine atom is leaving and the bromine atom is coming. Let us go to the final structure and we'll see the mode of vibrations. See the frequency, negative frequency is coming up at -323.67. -323.67, which corresponds to an IR frequency of 1200, and the Raman is very less, 3.02. Now let us see start animation by using the displacement vector. Now you see how the carbon atom is moving towards leaving and forming the bonds. Is that picture clear to you? That clearly an approach of chlorine to chlorine atom by is formed or bromine atom is formed. Is this clear? But while publication, how can I do this? I can never do this. Instead, what we have to do? We have to run intrinsic reaction coordinate, which was introduced by Fukui by predicted model. In this model, we have to give the input of the transition structure from the checkpoint file. Note that the transition state structure checkpoint file is the initial case for the intrinsic reaction coordinate. In this from the transition state have equal probability to go to the reactant as well as to the product. But which one is more viable, reactant or product? This reaction can be dictated by the thermodynamics of the system and for the whole reaction path. And this reaction path calculate the number of, it will contain number of different intermediate structures, and these intermediate structures is formed by doing some local optimization technique. How to get these optimization techniques? These optimization techniques are done by locally minimizing some structures in the whole path. That is the main algorithm of the intrinsic reaction coordinate for the molecular reaction path. Now let us see how to do this. Here is, as you have seen, the IRC input file is nothing but the transition state structure. Now calculation is given. Job type I should use IRC. There are three possible options, either in the both direction or forward only or reverse only. In the both direction, and note that you have to calculate the force constant 1. Here compute for more points n equal to 100. It is best to give n equals to 1000. That means it will do from 0 to 999 step, or 1 to 999 step. That means 1000 point will be calculated. More number of points I will have, I'll get more details picture of the whole potential energy surface. And using this number, more, if you give lesser number, you'll get more points. And reconnect the steps. That means I should instead of doing scattered path, I should try to make a continuous path, because in the potential energy surface I can have several structures, but all the structures I should not consider. I should consider only those structures which will be able to create a reaction path. Other than this, I should not get any picture. Herein we have written both directions, either forward or reverse. Note that if you give forward direction, it is not mandatorily that the computer will run only in the forward direction. It happens for several systems Once you have given forward direction, it will create a reverse direction path or vice versa. And general picture is also accepted forms. Then we have not given this. Method will be the ground state method, ground state Hartree-Fock method. Title is IRC, as it is totally your choice. If anyone wants to write anything else, it's not in computers business. And rest of the things we have already discussed. Submit the job as usual, and I'll open the output file. Now let us see. It have done 28 paths and check how it goes. Can you see how the chlorine carbon relation broke up and chlorine carbon bromine relation is built up? It is very distinctly clear. Now let us see what our plot suggests us. Is the plot visible? Intrinsic reaction coordinate, this red circle is moving, and along with this path, this end and that end are the reactant end and the product end. Can we do thermodynamics for that? Answer is yes. How to do that thermodynamics? What will be the energy of activation? Energy of activation is simply the difference of energy between ground reactant and the transition state energy, and 0 point corrected enthalpy difference between product and reactant will dictate us whether the reaction is exothermic or endothermic. Is this clear? Is this clear? These things are clear to everyone? Hello? Okay. By that, using that, I am closing my discussion here. If you have any confusion or questions, please feel free to ask me. Although this is very less time to show about the Gaussian C, there are several processes of Gaussian which you can, there are several scope of Gaussian software package, and you can do lots of calculations, and huge number of publications are observed still now, and I think it will be observed in future as well using the Gaussian software package. Here the Gaussian software site, and if you want to order or product order or you want to contact on that, just you will see the pricing. There are several options: academic customers, commercial customers, and these USA, outside India. You see there is a distinction: outside USA excluding India, China and Hong Kong. Academic special bundle prices. Check the price and open the xe.com to find out the exchange price of Gaussian and G16 and GBW16. That is $2025 if you want to upgrade from Windows version of Gaussian 9 and GBW5 to Gaussian multiprocessor 1400, and for single processor and multiprocessor it is $2025. That means it is more than 1,50,000. And if you want to communicate with them, their help desk is also available. Let me check. Otherwise, you can ask for help at the Gaussian.com. They will help you. Any question?
I think there are that much I have to check. No, so far there is no question, I think. Dr. Bhattacharya, your screen visible. Yeah.
Shall I stop sharing?
No, if you have anything to show, no problem. You have few more time.
No, not yet. Whatever I have shown already.
Things right now.
My Gmail ID.
Sir, your screen is displaying. Shall we close this? Sir?
Okay, better to close this. Now it is okay, right?
Stop share. Sir. Stop.
Yeah, now it's okay.
Now it is okay, right?
Yeah. So now thank Dr. Bhattacharya. I think okay. Any more question from the participants end? No, so I think there is no such question. So we will move for the second next session. Sumitra, do you want to show the TDDFT calculation? Have you seen or have you shown? Or,
Yeah. TDDFT calculations can be shown.
so I think
A small calculations can be shown.
yeah. So I think just it is just a small introduction.
Yeah. That is actually pending, right?
Yeah, TDDFT
Yeah,
calculation.
let's try with that.
Yeah.
To do
Yeah, do it for what are also.
time-dependent density functional theory,
Yeah.
before mentioning that, the density functional theory is a process where it can be calculated for the ground state system. It will not allow us to calculate the energies and properties of the excited state system, but using the time dependent variable, I can study the excited state properties, which involves absorption or the Frank Condon states, emission, or this emission will include the, is this echoing, emission states. This includes the fluorescence or phosphorescence. This kind of calculations we can do. How can I do the absorption and emission calculation? The process I'll show you. Let us try the absorption and emission of benzene molecule. As you have know that the absorption structure from the Frank Condon principle, absorption will not allow the molecule to relax. That means the ground state relaxed structure will be unperturbed during absorption. But while emission process will take place, this structure will be changed from its original ground state structure. Thus, how can I calculate the ground state structures to absorption? In order to do so, we have to use the ground state structure first and optimize the structure of benzene as usual process. Ground state Hartree-Fock 61G singlet, benzene ground state, and make it as a default as usual. Don't save because the ground state checkpoint file is of no use, and rest of the things I'm keeping as usual. Right? Benzene underscore GS. Let us do the calculations. In the absorption spectra, we will show the gas phase calculation as well as the solvent phase calculations to see how the solvent phase calculations, how the solvent phase incorporate the spectra, right? Our output file came up, and with that output file, this is our optimum structure. As you have seen, the benzene GS log came up, calculation will come up. Note that in quantum chemical calculation, we use the single molecule structure. Hence, this ground state structure corresponds to include that means this is 0 Kelvin temperature gas phase calculation. That implies 0 Kelvin calculation means other interactions are chosen, and gas phase means only single molecule. I have not considered the interaction between any other surrounding molecules. These are the ground state gas phase calculations meaning. If we say it is a process, it is a non-variational process, this ground state calculation term can be omitted. That means 0 Kelvin term can be omitted. But for Hartree-Fock or density functional theory, we should do that things, because ground state is only achieved at the 0 Kelvin temperature, not higher than 0 Kelvin temperature. Note that I have just written energy here. That means only our one energy is given. The ground state TDSCF is there. and Hartree-Fock I mentioned. That means either TDDFT, okay, let's put TDDFT calculations. But for DFT, we have to use a suitable functional. For excited state calculations, generally Cambridge relief functionals are used because, sorry, these Cambridge relief functionals can give us proper inclusion of the short range as well as the long range interactions. Basis state I am not changed. Solve for the states. It is made 6 is fine enough because I want to do the minimal calculations. If I do 6 states means from S1 to S6, S1, S2, S3, S4, S6, such kind of states will come up. If we click on the state of interest root equal to 1, that means if I do put 1, that means it will optimize the one first state only. But this is our not emission. I'm studying calculations of absorption. Hence, I have put number of states, solve for states, n equals to 6. Here I have written benzene FC state, that means Frank-Condon state, as it is absorption state. Hence, I calculate the structure benzene FCS. FCS gas phase. FCS underscore gas phase. Let us see. No. Just a moment, I made a small mistake. Guess I have to stop that default. No solvation also none. Because I have mentioned here it is a gas phase calculation. Right. So no solvent is given.
For TDDFT calculation, it will take some time.
Sorry?
I think for TDDFT calculation, so it will take some time for even for benzene.
Sorry?
For benzene, it will take some time, I think. So it is going on.
Yeah, obviously, but from benzene I can get at least structure, right?
Optimized structure is there, no problem.
For benzene, it will give some structure, but it will come up soon. It will be completed soon.
Okay.
Because absorption, the Frank-Condon state will not take much time. Frank-Condon states will not take much time, so just please have patience. These things will come convert soon. In the meantime, let us do make the input for solvent phase. Note that the model solvent, in the solvent phase, what I should, the model, general model is used, the solute is kept in the cavity of the solvent, and their interaction and the interaction between solute and solvent is taken into account using different models, like integral efficient formulation of the basic model of the solvent is the polarizable continuum media. In that context, the polarized system is kept in a solvent polar system, and that is dictated by the dipole moment of the solvent and solute. With that, polarized visible continuum model is taken place. Several other systems like IEF, PCM IPCM, that's integral polarizable continuum model, CPCM, continuum polarization model. These such point models are there. Generally, IFPCMs are used. And which solvent shall we take? We should take either ethanol or acetone. We cannot take the water as water model. Let us take acetone system and make the input. Instead of gas phase, Frank Condon, I will write solvent phase. Gaussian, in the meantime, Gaussian has been completed, and my next input is also ready. So let us do that calculations, and we will find what is our calculational process, right? Gas phase, this solvent phase, and the final one is the gas phase dot log. How to find out the structures? Go to the result and select on UV visible. Now see, there are several points. Check, there is a small minima. Here it is written excitation energy 214.53, oscillator strength is 0, so this will not taken. However, the maximum point is observed, the lambda max is observed at 161.32 nanometer with oscillator strong oscillator strength at 0.6196. Note that the epsilon term is now bit obsolete. Instead, the oscillator strength come up. If you want to go details of oscillator strength, either read the Lacroix group or read some other standard spectroscopy's book. You will find details about these things. Now, from the calculations, what I can find, the CV visible structures are there. We go to the result, open the file. Dr. is here, right? Note that for Gaussian systems, Gaussian can easily calculate the for biological systems the solvent effect, but note that you have to use Onium model, and the part of our interest we should take in an active site, active space, and the rest of the things are kept in the non-active space, higher level and lower level. Note that 6 excited states are shown here. Using that 6 excited state, the first excited state, note that is inert. Its value is 5.7792, is a high value. In fact, it will go even higher, 214.53, and the oscillator strength F is 0, spin is singlet, and the calculations is taking place from 20 to 22, 21 to 23. That means obviously it is from these structures it is shown that 21 is the HOMO, 22 is the LUMO. That means HOMO minus 1 to LUMO and HOMO to LUMO plus 1 calculations are taking place. One more thing we should use here, by summing up all the contributions at the denominator as a square terms. That means square of this term divided by sum of square of these terms. A square by root over a square plus b square. This is the formula. The energy, excitation energy the structure's energy is the minus 231, while the excitation energy is 5.7792, and the corresponding wavelength is 214.53. However, the lambda max value is here, which is also singlet S transition coming up from the group theoretical consideration, and the energy of excitation is very high, 6.653 eV. Correspondingly, our wavelength also decreased to 186.01 nanometer. This is also a inert state because A value is 0. Then the third state is the singlet A state, and value is again even higher, 161.32 nanometer, and the F value is 0.6196. Please note that this value is much beyond the experimental lambda max value of benzene. To do so, we have to tune to match with the experimental result. We have to tune the structures, or you have to tune the details of this, either basis set or functional, to get the proper value. I have opened this structure and see what is the form of this. In the meantime, this structure has been optimized, and let us open the log file of this. Using the same process, I'll check the result to find the UV visible structure and see how much it has been changed. Note that the value for lambda max was centered for the gas phase 161.32, and the oscillator strength was 0.6196 for gas phase, whereas for the solvent phase it has changed to 164.82, and oscillator strength also increased. That means the interaction in a difference between HOMO and LUMO is increased in this particular acetone solvent. What does it imply? We all are chemists. We always find for conclusion that some factor increases the gap. That means either HOMO got down from the level or LUMO shifted up. We can see from the output file. View file for this and view file for this. This one the FCS gas phase and this was the FCS solvent phase. Here you see 164, the third same excitation. These are mixed excitation. Same excitations, same orbitals are involved in whole excitation process, but let us make the difference. Energies. Alpha occupied energies, let us take. Here our alpha occupied energies. Thus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, 20, right? 20 is our HOMO, minus 1 HOMO. Now this is 0.30297. 1, 2, 3, 4. Now check here. This is HOMO value minus 3.3076. That is 0.30296. That means that much energy has been changed. The occupied level has been even more stabilized in the ground state. Whereas in the virtual state, 0.05 was the first occupied state, lowest unoccupied virtual orbital, and 0.056. That means 0.005. This much energy has been decreased. But if you check the difference, from that difference, we can find out how the energies can be formed or can be changed, right? We can further look at the invisible structures by checking the molecular orbitals energy plot. How can I get this MO editor? Go to the MO editor and you will see the 21 is our HOMO and 22 is the LUMO. Now can you see? If it is triplet, then 21, 22, this will come up. But since it is singlet, now you can see the energies differences. For both, let us open that. These two systems, this is for the solvent phase and this is for the gas phase. Check both the cases and thus get the structures. Now the thing is, can we find out the fluorostates of benzene? Answer is yes, but the calculation is time consuming. Hence, I skip these things as of now. Is this clear to all?
Yeah.
Arijitda?
Yeah, yeah,
Arijitda?
yeah. Are you getting?
You start presenting yours. In the meantime, let it will, if finished, the benzene optimized state, fluorescent state, then we'll do the calculations.
What you want to do for the solvent state, or which one, which calculation you want to show?
No, I want to do the fluorescence.
Fluorescence, I think it will be difficult to cover because we have no more time. It is almost 12 o'clock.
No, you start presenting.
Yeah.
In the meantime, if the calculations is completed,
Okay.
then I will show that.
Okay.
Right?
Okay. Yeah. 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 I got it.
Otherwise, it will be stopped as of now. Okay.
So, do you think it will be over
Any
by
other question?
10 to 15 minutes, Dr. Varchare? So, my query is,
Yes.
do you think it will be finished within 10 to 15 minutes?
I'm not getting. It will not finish by 15-20 minutes. It will, if so, then I'll show this.
Okay, that's why I'm telling better to stop now. If the candidates are very interested about the calculation of fluorescence, so then they should directly contact you, and your email address is there in the abstract booklet, as well as you may paste your email address here in the chat box. So I think that will be better because it will take time to understand also, and the calculation also. Because the computation of fluorescence is not
Yeah.
easier, not straightforward. You have to go by step and follow the a pathway and so on. So that thing, absorption spectra is very easier to explore. So I think it will be better to leave at this stage now, and only the interested candidate may contact separately. Okay. So, Dr. Ghosh, please take over the microphone. Dr. Ghosh, are you there?
Yeah,
Yeah.
yeah. Am I audible now?
Yeah, you are audible now. Yeah.
Yeah. So what I was thinking that Dr. Bhattacharya can run that program, and as it will not be finished in 15 or 20 minutes,
Yeah.
so maybe
Yeah.
yeah, if it get finished by half an hour or a little more than that, so during the discussion session,
We can.
maybe we can show the results over there. So
Yeah,
we
yeah,
have
yeah.
option for that,
Exactly.
and so for the time being, I think as one of our participant, if I'm not mistaken, it was Dr. Jishnu Chakraborty,
Yeah.
who was asking you during your presentation, if possible, or if we can manage in one session that we can show the docking, I guess, the online docking. So that can help really. So I would say, Dr. Bag, if you can foresee that it will be possible right now, then maybe we can do that, and then immediately we go to the discussion session, group discussion session. And yeah.
Okay, so I will take only 10-15 minutes to show a demonstration of online docking and few
Yes.
small things I can do. Let's start
Yeah.
sharing my. Is it visible now?
Yes, please.
Okay, not visible. Is it visible now?
Yeah, it's getting started. Yeah, it's
Yeah.
visible now. Yeah,
So
it's visible now. Yes.
yeah, actually there are a lot of programs which can be useful for online docking, but this is the Swiss dog, there is Jet dog, and so on. And also there is a online server which is known as docking server. So I prefer to use this, though previously it was quite easier to use as a guest. Now they ask some money for do this, use this. So I have a login. So just I'm going to the login, showing how it will occur. Yeah, this is you can do it the guest login also, but for guest login it will take huge time. So also if I am not a paid user, I only a guest user or similar kind of user. So it will take time, but I will show how you should go forward. And I have done a few docking previously, so I will show how the results will be look like, and how you can extract your result and so on. So for doing the docking, you have just click here, the right corner of your of the screen that is written in red docking. Just click on that, and then for docking, you need your protein and your ligand. So here you see there is two buttons. One is my protein and another is my ligand. So if you have protein, or you I am going to just for a small second. So there is option, so you can download your protein from the PDB database, or you can also upload the protein. There is option there upload protein, so you have to upload any PDB file. Otherwise you can just download from the RCSV. So here I have some proteins, so I am choosing, say, one is 6J, which is HIV capsid protein of P24. So I'm choosing this. Then I have to go for the ligand. Here also the similar options are there. You can upload your ligand, or you can draw. Here extra button is there, which is capable of just drawing your ligand, and that will be saved in the format which is required for this calculation. So we can draw the ligand. Otherwise, if in some cases with the protein, if the ligand is a say peptide or so on, so you can download it from the PubChem or any online servers where the PDF file is there. So you also able to download from there. So I have a few ligands here. So I am choosing one ligand. Just click the button. So I am using this. So now I have to look for the docking. So Actually, I have done docking yesterday, so it is pending. Including that, I have 10, so I have to remove it. Somehow. Otherwise, I can go forward because only as a guest user, I am allowed to calculate at the most 10. So I have to delete this. It will be time. Okay. So now I can start my docking. As a guest user, they stop you for 30 seconds before go for the calculation. And so for a free user, maximum you can do two docking per day. If you are a paid user, there are a lot of options. You can pay for 3 days, for 1 month, or you can have the option for annual subscription. So that will help you to do better. So now I'm going next. So first I have to choose any kind of ligand. I'm choosing this. Then click next. It is to be time. So then I have to select the protein. The protein I have selected. And then click next. Now your variables for docking is there. You can change the time state, the first one, and the G, Q state, and lot of variables are there, or Q run, number of G run. But as a guest, I can use only maximum 10. Any paid customer can use it instead of 10, it may use 100 short. But in general, a good ligand binding site always converts within 10 steps. So it is not very bad to use as a guest. And there is other for parameters, but I am doing taking all the default parameters which are optimized actually. So it is better to use unless you seriously need to change. So let's start docking. So that will appear a similar kind where they're showing your calculation is under process and waiting. So as an free customer, I have to wait for a month or 10 days or 15 days. But a paid customer is always allowed, and the calculation may be done within few hours. So as I am not a paid customer, so I can do the first. I have the not the first preference, so I have to wait for others' job to finish. So that's why it is not possible to finishing this work at this time. Instead, I am going to show you uh, what I have done previously. So, so I'm selecting this. When your calculation will be done, it will have these outputs. Okay, so you have geometry optimization, energy calculation steps, 2D plots, and the HB plots, also the methods and so on are given in the table. So this is your optimized structure, actually dock structure, you can say. So you can enlarge this, you can minimize it. This is my ligand, the green one, my ligand, which is binds, it binds to this site, and you don't know which are what is the binding site and so on. It could be seen from another tab, that is energy plot. Sorry, energy plot. You're seeing how the energy minimization takes place, and going back, here on the top of there is a table showing the free energy of the binding is minus 8.4 kilocalorie, which is very good. And its kinetic inhibition constant is 692 nanomole, but it's also very good. So this is both the binding energy, the inhibition constant, and then you have the binding frequency on the right of side is 30%, which is not very good. So there is a binding frequency, that means the chance of binding, and also you have other energy values. So now I'm going for the 2D plot, where it is very easy to see which residue of the protein is binding, in how it is binding. Here you can see that the tyrosine 59 and glutamine 63, these two binds through a hydrogen bonds to the ligand, and there is a polar interaction of arginine with the arginine, which is 62 residue, arginine 62, and there is few hydrophobic interactions. So they are all, those are listed in the here, the hydrophobic. And so this structure is clearly showing this is the structure of the ligand. So this is the structure of the ligand, and this is the different part. That is only those amino acid units are shown here, which have the hydrogen bond and how they are bonding. So you can see they do two amino acid residue do the hydrogen bonding, and others are have the polar interaction or hydrophobic interaction. They are showing in a different way. So if someone needs the Havu plot, which actually show there is another thing, that is interaction table, similar to the previous, but here more details are there, and we have the JMOL view. So how the nearest amino acid residue of test is shown here, and the Havu plot, HB plot, is actually show the binding site of the total protein. This is the total protein, and this part of the protein are near to the docking site and to the ligand where it is. And for your reference, how these calculations are done and the reference for this are given in here. That is method, and your gallery is shown the docking structure again in a different mode. So with that, I can stop here for the docking. So you can docking with this, the docking server. Now I want to show one thing, the calculation using mole inspiration. This is another online software. It's very cheap actually. Cheap in the sense that not rigorous calculation would be done, but you can draw the ligand structure and predict the biological activity. Just click on the biological activity, then it will show the activity of this compound in GPCR as GPCR ligand or enzyme inhibitor or protease inhibitor. This is general. These calculations are actually done through the QACAPR, that is means the qualitative structure activity relationship. So these are different kind of biological activity, but these score are not very good. So you can change if you want to design your compound, you can change and check whether it is improving or not. Let's say we delete this. So I'm trying. I don't know whether it will be effective or not. Just testing. Let's say it is better than the previous, because you're saying these values are coming positive, and any value more than 0.5 will be good for that purpose. So let's try if we have any good value. Just trying blindly. Yeah. Now see, we add CH2NH2 group, and that improve your biological activity with some values of 0.37, 0.37 for GPCR ligand, 0.37 for ion channel modulator, and so on. So now let's try with another case. So just I want to delete this person. This may not work, may reduce the activity or increase the activity. Just try. Yeah. See here, ion channel molecular activity is increased by some extent, but other activities are going down. So let's and add one wedge group here. See here, this molecule has beta biological activity, at least four uh, activity. All values are positive, and so in this way you can model your compound before going for a serious calculation by as a docking server or any kind of any calculation. You can just model and check whether their activity by the qualitative structure activity relationship, that is actually mainly the Chrome 4 calculation, whether it is effective or not. You can just check. Though these results are not always excellent, but it gives you a hint that it may be a biologically active compound. You can have other calculation also for calculate properties. You can calculate using this, mainly the log p value, which is very important for any drug calculation, drug calculation. The log p value. This is the log p value of the your compound. For this compound, is 4.23 is good enough, and you can calculate the volume and the surface area also. It is also important for surface area because for docking, we actually docking when we are docking a molecule or ligand with some protein, it all the success of that docking, the energy value also depends on the surface area. So if you want to calculate the surface area of your ligand, it is possible to it is possible for molecular inspiration. You can do calculation using this at the volume of the molecule, and it also showing your whether your calculation the model structure is viable or not. If you have any red color in your screen, these values, if you have any red color, then your structure may not be physically possible. Otherwise, it is okay. You can get extract your geometry of these molecules by clicking here. There is also different possibility. You can use this. You can um, you can have the mole file uh, to extract the geometry of this system. Use the background as if you want to know why. So this is very not so good on, but it helps you for drawing the ligand and predict its biological activity. There is another software which is actually good. It is the Chemosophia, the software name. I have a login here. You have to do a login here. It's free, and with that you can calculate a lot of things. But your ligand has to be put it here. You can put the ligand through HDF file. There is a problem because the different kind of file structure, chemical file structure. So there is a lot of online software by where you can use change your chemical format. So you need the SDF format for this calculation. Here I have the molecule is uploaded here. Just click on it, then go. There is chance of calculation. So I'm going for one molecule calculation. There is also option you can optimize this geometry and then go for calculation, but I am going without optimization because my component is already optimized. So I am going to only calculation. So here you see green and yellow as well as no red is there, but maybe red there. It shows for green it is easily available calculation, and YOLO software is available under some conditions, and it means software is not available for your compound. There are a lot of calculation you are available. So we are going for calculation of biological activity. Just clicking here. Here you can see that okay, lot of test you can do with your compound. You can calculate for antibacterial activity. There is also the option for anti-tumor alkylic activity, anti-tumor topoisomerase 2 inhibitor activity. A lot of things are there. You can do for tuberculosis dihydrofolate reductase inhibitor activity. Here, anti-tumor, anti-myototic activity. A lot of things are there. You can do your according to your choice. So there is a lot of things. I also have see the metabolism of this your compound is also possible to calculate using this software. Metabolism of your compound to CYP43 and CYP43 to the 6. So you can calculate the probable metabolism path of your compound or of your ligand using this. So now I'm going to show you a small calculation. Say HIV on protease inhibitor activity. Let's do this. I'm doing this. Only one calculation. You can do for various calculation at a time. I'm going with a single calculation here. You can choose different also. You can choose this one also, but I'm not going for that. It will adding more and more calculation will require more and more time. So I'm just doing only a single calculation as HIV on protease inhibitor activity. So go to the next step. Yeah. So procedure to check out. So then it may take one of time is showing as 1 minute. So that means it will be good enough. So you can go for it, and price is 0, so we can do it freely. Okay, now let's compute. So it is saying that computation is there already done. So computation has already done. So just open this. It will download it, and open this. So it is showing or not? I think yeah, it is not visible. I think this window. So if you download your zip file and then open this, then it is written as the probability of your calculation. That is in our calculation, it is showing the 0.243. That means probability of the activity or probability or activity of that molecule we have taken as a HIV on capsid inhibitor is only 24%. That means it's not good one. But if your molecule is good enough, so you may get 60%, 70%, or even you can 100% chance of activity. So in this way, we can calculate this. So now I like to stop here. I have shown you three different online softwares where you can calculate the biological activity, the docking, and so on. And before closing, I want to share one thing. Uh, uh, this is the chemistry at the rate of MAKAUT, which actually maintained by our department. And all the 5-day lectures, YouTube links are available there, and upcoming programs will be updated here. So who are actually interested may join this Facebook group to follow our activity in near future. So thank you all. With that, I am stopping of sharing. Dr. Ghosh, please.
Thank you. I'm audible, right?
Yeah, yeah, you are audible.
Yeah. So thank you, Dr. Bag, for taking your time and preparing yourself for the upcoming question from the participant and showing them hands-on how to do the online docking things and the associated stuffs along with this one. I hope our participant who had the question from the query will be happy enough to with your response. So thank you again. And I would like to thank you again for showing the Facebook page for the chemistry at MAKAUT and the progress that we are uh, doing or having, and being a faculty of Department of Applied Science and working on the course of MSc in Applied Chemistry, which is very new. It's only 2 years old right now. So thank you very much for sharing that page as well. Thank you. So I think what we have next is uh, uh, now we were scheduled for the group discussion, I
Yeah,
think.
yeah, yeah, yeah.
And yes, so as I can see over here, we have Dr. Chakraborty, we have Dr. Bhattacharya, and I think we miss Dr. Bag, Dr. Monojit Bag
He
right
will
now.
join later. Yeah,
I think he will be joined in due course. And I mean, if you think that we can take 10 minutes of break, because maybe we can cut short the discussion session in 1 hour. It's currently it's 12:20, right?
yeah, yeah.
Or yeah, so maybe
Yeah,
10
maybe
minutes.
yeah, we can meet at 12:30
30.
when
Yeah, yeah.
Monojit
Yeah,
will
so
Start at
10
12.
join.
minutes of break for the participants as well, and we meet at 12:30 and we start the discussion session. And from 1:30 we will have the valedictory session. And I wish and I believe that our Honorable Vice Chancellor sir will be there to address the valedictory speech. And so uh, we must finish the discussion session before 1:30. So I hope it is not big issue. It will not be. And just thank you again, all the panelists, the esteemed panelists, and the participant for taking your time to join the sessions of day 5 or 5-day online faculty program. So we will meet in 10 minutes, and it's just a break for 10 minutes. And from 12:30 we will start the discussion session. So whatever questions and queries or whatever you want to know or you want to share your thoughts, we can have the discussion regarding all the, I would say, 4.5 days so far, and the topic that the esteemed speakers they or the researchers they have disclosed or they have shared with you. Just take the advantage of this one, and we will see at 12:30. Sorry, 12:30. Yes, thank you.
Thank you. So we should start, join at 12:30.
Yeah. Prem, can you please put the page that you always do? That was so nice at the break page.
Hello, Prem Kumar, are you there? Hello. Yeah. So we can start now. It is 12:35, so we can open the session now.
Yeah,
Yeah.
maybe. So, shall we just?
So then, yeah. So just thank you again.
Your sound is cutting.
The break. And this session we had specially for we wish to have that one in for the whole 5 days. Hopefully, is it coming right or it's
No, can you please
hello?
repeat actually? Yeah, now it's fine. It was vibrating actually. Could you please?
So now it's okay, or
Now
Yeah,
it's
now
fine.
it's
Yes, yes.
yes, okay. So yes, so yeah, we are very end of the 5 day program. Now we have the only one discussion session with a group discussion, and our esteemed panel members will be here to interact with the participants and also to interact within themselves, so that can help to build some further collaboration and to enrich the scientific knowledge of individuals who belong to the fraternity of science. So in this session, I would like to invite Dr. Sudip Chakraborty of IIT Indore to please chair the session.
Okay.
Dr. Chakraborty, please.
Yeah, thank you, Dr. Taposh. So I think it's really nice. So maybe Monojit would join us at some point, probably. So we can start in the
Yes,
meantime.
yes.
Okay, excellent. Okay, great. So I think it was wonderful 5 days sessions that we had, and I think I'm pretty happy the way it has been organized. So first of all, thank you, both of you mainly, and Dr. Arijit Bag and Dr. Taposh Ghosh, and also the other faculties were giving the lecture. I couldn't attend the other due to my time constraint, but yeah, I mean it was really nice. So maybe the discussion could be started with directly with the participants. Maybe we can start with their individual feedback, what they have thought, if they have any questions, and if I mean, anything that they can kind of, they can feel free to kind of share here. So, and then maybe we can go to the panelist member, and at the end we can try to talk about, what's our future roadmap from here. So that would be a better way. So maybe if can we just start one by one, or you can take care about the attendee.
Okay, so in that sense, from the participant, I'll request them to come forward and, as Dr. Chakraborty said, to express their views and their opinions regarding the FDP. And also they can discuss if they find some topic more interesting to themselves, and if they have any queries or anything to discuss with the panelists, please. Maybe you just
For the
raise your hand and we can,
participants, for the
yeah,
participants, it is open answer session, and they can give
yeah.
their feedback by raising the hand or posting in the chat box. We will be giving the opportunity to talk with our eminent speakers. So feel free to ask
Exactly.
anything and any information regarding the topic and the scope of this topic also.
Yes.
So we are now requesting to all participants to kindly come forward and give their some informative talks. And
So I can see there is one hand. Yeah, Dr.
yes,
Jishu
Dr.
Chakraborty.
Jisu Chakravarti, sir. Yes.
Am I audible to all of you?
Yeah, you are.
Okay. First of all, I like to say that it was a nice journey to discuss almost 1 week uh, in the teaching learning process. And being a faculty of Tamil Institute of Engineering and Technology, my college is nearby Panagarh, Durgapur. and now I'm in the campus, and I got this opportunity and tried to avail it with my best possibilities, and at this pandemic situation, even in this tough condition. So it was a good opportunity for me to learn so many things. Actually, I am an experimental chemist, rather biologist, you can say, because my field of work was structural biology, protein chemistry, starting from the protein isolation, purification, structural parameter studies, and its folding, refolding, unfolding kinetics, aggregation in conventional and non-conventional strays. Different issues, that was my topic during my PhD work. And also, I worked on the nanoparticle protein conjugate systems also. And in my lab, or in Jadavpur University, under Dr. supervision of Dr. Chandra Haldar, the work is going on. Collaboration is there also. But at that time, when I was working in my lab, I did not have the opportunity to get this computational part and all these things, uh, such expanded and extended mode. Now the scenario has totally changed, and probably this COVID situation is uh, pushing us on towards to go with the existing and developing systems with the computational biology part or computational chemistry part. And definitely it was a very informative, and so many things and so many doubts and confusion that I had, that you have cleared. I'm pleased and I am honored to be associated in this journey with such a professor from different universities, starting from my own West Bengal, MAKAUT, Professor Bag, Professor Ghosh, and I'm also thankful to Professor Datta and Chakraborty and Bhattacharya, so from Sikkim. So I hope this is going to be the good association in near future, so that we can collaboratively, we can work, and each and everyone has their problem. Problem means scientific problems. That problem should be addressed, and a platform should be made through which this problem could be addressed and solved. And with this anticipation of the future of the computational chemistry or communication biology, whatever is the motive for all of us we're doing or trying to do. With all my best wishes, I extend my cordial thanks to all of you, and stay safe, stay home, stay fit. That's all from me.
Thank you, Dr. Jishnu. I think it was really nice. You have putting that. I think one of the things that you have put forward is this one common platform. That could be something really we can envisage as well. So maybe if I mean Dr. Bag or Dr. Ghosh can think about, maybe if we can have kind of a common group mails or something like a group way, so that whatever we are publishing or whatever we are project we have, wherever we have any collaboration which is required, maybe anybody can kind of put it forward there. I mean, they can post it there, and if anybody interested, then they can directly talk to that particular person. So I mean, it will be like we can make, I mean, this shouldn't be the stopping point of this nice journey that we have started. So maybe we can kind of make a group activity, so that maybe you can take care of that thing. If you can have a group where anybody can post something there, and I mean, anything like their nice paper, or if they want to kind of collaborate, or I mean, if there is something which they want to share, and then the appropriate person could kind of come forward and talk to that person individually like that way. So that could be one thing that we can kind of think about. Yeah. So maybe Dr. Ghosh can,
Definitely.
or Dr. Bhav can.
Yeah, definitely, Dr. Chakraborty. This has been a vision for us as well. This should not be the stop of the FDP. This is just the beginning of the interaction with you eminent faculties. across India from different IITs and who are already known in their field by their own right. So it's our privilege to be connected with you all guys, and also for our participants, I believe too. They will be more than happy to have a group and have the opportunity to interact with you. Maybe some kind of group we will think of a common platform as you suggested, and it will be beneficiary for all of us, I guess,
Yeah,
to
and even
spread the
also,
computational chemistry.
exactly.
Yes,
Maybe we can also think, I mean, if we can even post some kind of vacancy if our lab is there. I mean, that would be another thing that
yes,
one can really be
exactly.
useful for, because if there is any PhD or postdoc vacancy, one can always put there as well. So, and it may not be just
Yes,
limited to
yes.
this 29 participants right now, but it could be, we can always explore more people if they are kind of doing that. So that could be something that we can look.
Definitely. This will be so gracious of you, and this will help us a lot because our MSc in Applied Chemistry program that Dr. Bagh just showed few minutes back, the slide, we started off last year only, and the emphasis is on computational chemistry. So definitely, we would like to be the most beneficiary of this FDP if our students can have the opportunity to work in your research groups in projects or as a PhD student. So this will be something for them definitely,
Yeah, so
and to
maybe
have a
this,
bright future as well.
yes,
So
one thing maybe we can kind
yes,
of, so maybe Dr. Bach,
definitely.
you can kind of coordinate, and if you need any input from our side, please let me know.
Yes,
I mean,
Obviously, obviously.
yes.
I'm actually trying to build up such kind of things. So I think
Mhm.
within few days we will be able to collaborate, make such a platform where we can connect all of you with
Mhm.
many more participants and many more students from different universities and colleges.
Yes,
So
yes.
actually, it's a journey, beginning of a journey. I can say. Because success is not a single event. Success is always a journey. A
Yes.
path. You have to travel a path. Only then you reach to a success. So, okay.
Yeah. So I think, yeah,
I
that,
think from the participant point, we have one more raised hand from Santanab Giri. So Prem, if you can please allow him to talk, and he can share his thought and discuss with the panel.
Yeah, good morning to all of you. Although it's already noon. So anyway,
It's okay.
so I am working in Huldia Institute of Technology in Applied Chemistry Department. So I am a computational chemist. So I'd like to thank the organizers for arranging such a nice FDP program on computational chemistry. All the topics I really enjoyed, and some topics I actually don't know much, like Dr. Chakraborty and Dr. Manojit Bak discuss about that perovskite, solar cell, and all these material science topics. But I really enjoyed all those topics. I hope within the next week I will be able to listen both of the speakers, because we are going to conduct one webinar on the nanoscience and nanotechnology. Uh, Actually, I want to discuss one topic with Professor Datta, since he is a developer of Orca. Actually, I am familiar with Gaussian, and I am currently working in three different areas, like building blocks of little bit high reactive alkali and halogen, as well as that frustrated Lewis pair for the small molecule activation. So recently I got that DST project out of that. But since I am not very much familiar with Orca, so I'd like to know certain things about Orca from Dr. Datta. That last 2-3 years, actually, I am trying to model an excited state proton transfer reaction between the model DNA base pairs. I have searched so many literatures, and people are actually giving some kind of transition state of excited state geometry. But really using Gaussian, it's very, very hard to find.
sometimes the proton transfer happens so fast that we could not able to trap the transition state also, whatever facilities we provided in Gaussian. I would like to know whether there is some kind of trick in ORCA so that we can able to locate such type of transition states to facilitate that excited state proton transfer reaction mechanism.
Okay, so you asked me something what is very close to my heart. I work on DNA basis. Although not excited state, I generally prefer to study electron attached states than ions. But excited state, they have very similar features with excited state. Now, let me tell you the issues. First of all, when you are doing a potential energy surface, many of the time in surface, what happens is that we are chemists, right? So we
Yeah.
prefer to think that one electron in one orbital. That's what a chemist view of molecules, atom, electronic states. But what happens is that when you do potential energy surface, sometimes situation arises that it's not actually one configuration. It's a linear combination of configurations. So that means if you use a single reference method where you start with a one determinant, like a chemist way, molecular orbital theory, that is going to fail there. And that, of course, is actually a problem. Second thing, you need to, while drawing a potential energy surface, you need some kind of a bound. You want to make sure that your saddle points are properly modeled. Now, in a DFT method, that's much more difficult because DFT is not variational. So you need a variational method which at the same time can treat this more than one configuration. Of course, best case scenario is full CI. If you can do it, then it's the exact solution of the Born-Oppenheimer Schrodinger equation in that basis. But of course, you cannot do full CI anything beyond a small diatomic molecule in a very moderate basis set. So then the second option is to go for multi-reference method. Basically, the complete active space based methods, which are essentially a full CI in a limited space. So that's the kind of methods you should use. Now, what are the caveats? First of all, whenever you go to these sophisticated methods, your results depends upon a lot of parameters. So you have to really, like, making the input file is no longer a black box. It requires a lot of effort, and many of the times you get bumpy surfaces. Second thing, the question, you are looking at a phenomena which you are supposing is going through a transition state. Sometimes locating transition states can be problem. ORCA has a very good transition state locator now, so it uses the large elastic band method, and it's pretty good. But again, to study the proton transfer, what I would have done in your case was that I took the final structure and initial structure and just generate a linear transit. Of course, this does not give me it gives me some idea of the mechanism, does not give me the exact barrier height, of course, because I am just doing a linear transit where my potential energy surface is multidimensional. So what I get is an upper bound to that activation energy. So I would start with that picture. Remember, when we do computation chemistry, it's more easy to understand, interpret, then go to the exact number. I can calculate 1.48937 digit kilocalorie per mole energy. But actually after one, nothing has any meaning because they are beyond the chemical accuracy. So even if I put those numbers, nothing comes out of it. So I think to me, it's more important to have a qualitative picture. And I always prefer, so generally the good idea is to start with a model compound. If you take a big molecule, of course, that is more close to reality. But the problem is that in big molecules, the details are so much that everything gets blurred. You cannot see what you are looking at. So it's always a good idea to take a small model system, try to understand what's going on there. And then upon your understanding, you should take a bigger system and go like that. Of course, and remember, models are very important in quantum chemistry or computational chemistry. So I reiterate the statement that a model is a lie. So it's of course a lie. It's not the real system, but it helps you to see the truth. A model only helps you to see the truth. It's not a truth itself. So I would suggest you to use a small model system and try with that. Of course, if you have explicit problem, you can write to me, and I think a better place to write is that Orca has a very nice forum. Like the kind of forum we are discussing, Orca actually has a forum. So where you, if you write your problem, one of the users, or if nobody answers, one of the developers will answer to that. That's how it works. So it's a two-way advantage. How it works, so the user gets to know the answer of our questions, and we get to know what is the problem with our program for free. Somebody complains, so we come to know. So it's a win-win situation from both sides. That's how we operate. I hope I give some answer to your question at least. If you have further questions,
Yes,
you can ask me.
yes, definitely, definitely. Thank you, thank you.
So thank you, Dr. Giri, as well, for sharing your thoughts and clarifying your queries. I guess our speaker has answered you and satisfied you with the answer. So we had one more in the chat box. It was someone, Sandeep Joshi, who wanted to know, can you send the link of Gaussian software? I think this has been answered by Dr. Arijit Bagh. To go to Google, and then you can have the link for that thing. So yes, so this has been answered as well. And if anyone of our participants want to interact with our esteemed panelists, please raise your hand.
So I'm seeing Pramod. Is it for long time hand is raised?
Yeah.
Is it a technical problem or is it?
I think last time we had reached him and it was
okay, so probably
no
it's
question.
technical issues. But yeah.
Yeah, I guess. So, I think Dr. Manojit Bagh, can you hear me?
Yes, I can hear you. I'm just listening.
Yeah. So as
I'm sorry that I had to go somewhere and I could not join on time. It's a bit late.
no,
I had
it's okay. It's okay. I think if you have missed something, Dr. Chakraborty will be happy to share that thing with you. So don't you worry.
Yeah.
So
Anyways,
I just had
we are already collaborating. So
yeah. So that's why I said that. So pardon me. So just a query for me. I don't know, it may sound stupid, but Dr. Anand Datta, who was one of our speaker as well, he said that no question should be stupid, only the answers can be. So relying on that, I am asking the question. So the question is, do you foresee that at some point of time in near future, the organic photovoltaic materials or solar cell materials will meet or will hold hand with the perovskites and we can have some blended materials? Do you foresee that thing in future?
I should say yes, because I don't disregard or discard this organic solar cell yet, because this still has the potential. If you look at the efficiency wise and the fabrication wise, it is still quite efficient, in the sense like people have reached up to 15 to 16%, and tandem cell
Yes.
definitely there is a possibility. And in fact, I have worked with perovskite polymer tandem solar cell, and that used to be very early days, though maybe now, like if I look back, maybe we could have done even improved efficiency that time also. So especially like when you look at the indoor light recycling, right? So today I was also talking about, so there is a even like Great Cell Group is working on that areas, because all these third generation solar cells, especially like perovskite solar cells, maybe organic solar cell, even dye-sensitized solar cell, they may not have the stability of 20 years like what silicon solar cell has. But definitely you can look for all these organic perovskites or dye-sensitized solar cell for alternative applications. Like it could be like a window curtain, maybe like a small panel inside your room to power lot of small equipments. Like you can start with say wall watch, or maybe some small toys, calculators, even like mobile phones and so on. So you can use that where this technology, this third generation solar cell could be really helpful. And even right now, what I see is organic solar cell maybe even more stable than the perovskite solar cell. So earlier we used to think organic solar cell doesn't have the stability, but looking at perovskite, I still feel okay, organic solar cell has better stability now compared to the perovskite solar cell. Definitely, like people are working on perovskite to make it more and more stable. Maybe in future we will have more stable solar cells, but it is still there. I mean, we cannot deny that. And a lot of people are looking at fluorine-free solar cells, which can be more stable. So still, people are
Yes.
working on organic solar cell. I would not say like you should completely discard this technology yet. So it still has
Okay.
the.
Okay. Thank you, Dr. Bag. And one more question to all our esteemed panelists. From my point of view, that considering, is there any barrier or something? Because I don't have that much knowledge of the computation as far as your domain is concerned. So is there any kind of molecular weight or something that limits the computation technique for calculating the organic molecules? Like if you have some 4 or 5 fluorine molecules attached with porphyrin, so the molecular weight gets a hell lot and around 5,000 or so. So is it also possible for those kind of molecules to have the computation and to see whether the band gap thing, or what are the feasibility of that kind of molecules before we do the synthesis? Because it takes a hell lot of time to synthesize or attach your 4 fullerenes, if and it will be much more difficult if it's a asymmetric molecule. So that take a couple of months. So considering the wasting of time, can computational chemist can some put some insight into that before you go to there, just check whether this kind of molecule will at all be feasible to perform or not in terms of the solar material, solar cell materials, or photovoltaic materials, rather say.
So I think it's mostly the number of atoms that you're talking. I mean, the molecular weight is actually going to that direction only. So as far as we do the DFT calculation, and also some of the DFT calculation, yeah, I mean, there is a bottleneck there. So there is a number of atoms which is constant there. And also if there is heavy element there, you need to consider the relativistic spin-orbit coupling, which is also kind of computationally quite expensive. So I mean, I don't do this kind of thing, but I know people are doing a lot on QMMM. Maybe the other panelists can talk on that. And I think in that way, one can always reach to that. Like when you have a force field calculation, maybe Dr. Achinto or Dr. Arijit can shed light on that. So but only with normal DFT or QM, it could be really difficult actually.
Yes.
So you need to go for QM and MM approach for that thing. Yeah.
Thank you. Thank you.
Okay, let me tell something here. So, of course, the with the increase in modern computation facilities and with the modern software packages, the numbers are always flexible. Like when I started my PhD, and of course I was working with very accurate method. To me, a big molecule was a benzene ring, and these days I think benzene ring is a small molecule. So small big capacities, everything depends upon how much facilities you have, what kind of software you are using, what kind of methods you are using. If so, the mostly commonly used method is DFT. And generally, if you have a very good program package and have superior facilities, then you can go up to 300, 400, 500 atoms for, like, if you want to just optimize it. If you want to just do single point calculation and want to use pure functional, not interested in hybrids, and does not picky about basis set, you can go up to 800, 900,000 also, but in a very small basis set. But beyond that, it's almost impossible. And of course, we are not from a very privileged country, so none of us have a supercomputer to our own. So in a real life situation, that's the limit. Now, what's going beyond that? One approach is, of course, going for QMMM. That's a good approach, but one of the problems with QMMM especially is that your force field has to be good, and that's not a black box. Like you're like, if you really don't understand how the force field needs to be parameterized, then it's very difficult to make sure how will be the result. And I'm of course I'm not good at parameterized force field, so I just search the literature and see whatever people tells good. I only use that. So my understanding is force field is very limited. One of the good compromise is to go for semi-empirical methods. Although because of modern computation chemistry softwares and computation power, we have almost written off semi-empirical methods. But actually, semi-empirical methods can give you a lot of mileage. In a sense, it is like a force field because it's parameterized. So you parameterize your two electron integral by fitting some experimental parameters, but they are more systematic. So the empiricity is less, and you can do a lot of corrections for the systematic thing. So these days, especially this tight binding DFT methods, which is a semi-empirical method, of course, are becoming quite popular. So if you see the work of Stefan Grimme, his XTB, this kind of fullerene system, you can actually run a calculations on your laptop, and you ballpark know what is the accuracies and what will be the result. You can ballpark judge. Question is is it always work? No, it will not always work, but for most of the cases, it's going to work. So what is going to do is that from 100 candidates, it can reduce it to, let's say, 10 or 20 candidates for your synthesis. What it cannot do is from 100 to 1. That's still impossible. But it can give you a lot of mileage, is that you can get a good understanding out of it. And the difference from a force field parameter to the semi-empirical thing is that semi-empirical things are more chemically driven. Like one of the most easiest semi-empirical things what we are generally taught in chemistry is the Huckel theory, and that's totally come from chemical intuition. So semi-empirical theories can give you a lot of insight into it. So for systems which is beyond 500 atoms, I would always prefer to go for a semi-empirical theory. Remember that, and also if you ask me what is the limitation in a current computational field, I would say the limitation is our imagination of our mind. Like if we take, so we need to decide our method, our model size, depending upon what kind of facilities we have and what exactly we are looking at, what phenomena we are looking at. If I am looking at a energy difference of, let's say, 50 kilocalorie per mole, and for that I want to do a very sophisticated couple cluster calculation in a full complete basis set, it actually has no meaning. Because the energy ranges are so high that even a DFT method as good answer as a couple cluster. So it does not really make a sense. Again, what I have seen that more computation facility you give to people, the more misuse people start to do. So they submit any job, and whatever job they want, people with small computation facilities generally use their brain more judicially, and they get a more of understanding out of it. And I would again say running a computation chemistry job is a clerical job, it's not science. Interpreting the result is science.
Yes, yes. I think I fully agree with that actually. So
thank you
I
for the
think
insight.
the students are also, I mean, people should be more kind of cautious. Like if they're just giving some cluster, they just submit jobs quite randomly, not even knowing that they just do like 10 different possibilities and 10 different jobs they submit. It doesn't make any sense actually. So yeah, I think, yeah, I fully agree with that. So another problem, I mean, leading to that particular topic is the computational time that we're having. So I'm not sure about MAKAUT, if you guys have any kind of computing cluster that you have there, or we can kind of discuss more about that. We can kind of try to make a joint computing proposal and we can submit somewhere. Maybe Dr. Arijit can talk about that. Maybe working on particular area there.
So far, we haven't such competition facility, but we think within very short time we'll be able to acquire these things, and then otherwise we can collaborate in different ways by sharing our thoughts, by proposals, and so on. And we can write projects for that. That is not an issue. I think that will be very helpful to bring computational facility in our institutes also. And okay, I am hopeful for that.
And I think you are also talking, we are discussing about a journal. Like, can you have some kind of journal from our community here? So maybe you can
That is
shed light on that. Yeah.
actually that is necessary, I think. So nowadays every university has journal, every institute has journal, but See, if we look around the world, there is no good journal from India. So that there are a lot of issues behind this, and not also the good computational program from India also. I think Dr. Dotto is laughing. I think he has previously he had that such project. We should do a computational program from our end. So that is tedious, I know, but we can think about that, and also it needs some initiation from some end to have a good journal with some the reputation, as well as we have to devote ourselves that in such a fashion that we can publish at least one good paper in that journal in a year. And then I think if we try to publish at least one good paper in that journal, in our journal per year, after 2 or 3 years, or after maybe after 5 years, it will be visible to other researchers around the world, and it will, may have the good citations, good impact in this scenario. So okay, we can try it, I think.
Mhm. That's
And
nice.
So I think I should add it here. I mean,
Yes.
probably the biggest drawback India, I mean, like from India, we don't have high impact or that reputed journal all over the world, like what, like other, even if you look at the Korean journal or Japanese journal, they are much more popular than like what we do have. So it is probably the policy we don't adopt. So normally people look at, like when we publish any Indian journal, people will, oh, they are not able to publish in good journal, so that's what people are able to publish in Indian journal. So that mindset probably has to be changed. And I guess only if all the institute, like including IITs, ISERs, and NITs, they make a policy that okay, you have to publish Indian journal for your, say, promotional work or your academic career, you are forced to publish, then definitely this journal will have much better impact. And maybe in future, this journal will be popular in the science community across the world. So I think there is a policy making issues. I mean, it's not about like publishing in Indian journal, but that has to come from the upper level, right? I mean, institute have some policy that okay, you have to publish at least some Indian journal. So like year, or at least within or maybe a 2 year or so. Then I think this journal will be this is possible. Otherwise, uh, people will go for the international journal without knowing what is Indian sciences needing, basically. So that I can say.
Yeah. Yeah, I think I agree with that. Like, unless you have been forced, you won't do that. And that too for the promotion. So, yeah, I mean, that's one of the thing that we can go. I mean, if you can at least publish one good paper in those
Yeah, that
journals.
is only way I can see that Indian scientists
Yeah,
working in this IITs, ISRs, they will be able to, they will publish. Otherwise, no one is going to publish in Indian journal
it's true.
unless we
So,
force them to publish.
yeah.
I'm,
Yeah.
I'm a
It
bit
should come from the
afraid when you are forced with
reputation.
something, then you maintain the quality or not. I'm a
No,
bit
that
afraid
is
of
what
that thing.
definitely see. Quality will come unless you are forced, because otherwise, what will happen is, okay, this work has not been published somewhere. We just submit it to Indian journal. That should not be the
That
case.
should not be the
Yeah,
case. Yeah.
You
that
have
will
to
be
publish your
horrible.
best work in the
That will be
Indian
horrible.
article, Indian journal. That is
Mm.
Yes,
only,
yes, yes. Then only
and
we can have
definitely
some
we have
quality
the
journals from.
what do you call this, expertise to see whether this article, whichever you say, like it will be published, this has the credentiality or not. Right?
Yeah,
Only way. I mean, it has to be peer review as well.
yeah,
Mm.
yeah, definitely.
Journals.
Yes,
I
yes.
think nowadays most of the Indian journals are belongs to Springer publication, Springer Nature publication. So that is a platform actually. So if it is properly tuned, I think it may happen within few years, because now the platform is there. The Springer Nature publication has a good other journal publications. So that is there. So the Indian Academy of Science.
Even like you have Nature Asia or we have Nature India as well, right?
Yeah,
Yeah.
Yeah,
But we don't publish
NPGS is
research
there.
article there. So
Mm.
probably we need to publish more research article in these areas, and then only leading experts in this field can take the lead. If they start publishing, probably other people will start publishing.
Yeah.
Without their contribution, probably it will not be possible in the future.
It should start from the so-called reputed scientists, and if they start to publish frequently, then other people also come to publish.
Yeah. Yeah.
For example, because whenever we submit a journal to some reputed journal internationally, and sometimes they like transfer it to some news journal, and then sometimes they oh, this is a news journal, we will not publish. That is the same mentality, right?
Yeah.
Because recently it happened, like I submitted one article to Journal of Metal Chemistry A, and then say, okay, maybe it's
Materials
okay, but
advance.
we can, yeah, materials advance. Yes,
Advance.
exactly. You know, exactly. And these are all open access
Yes.
journal, and they think like, okay, from India, you guys are trying to publish, so you will be able to, you guys are hungry to publish, basically, right? I mean, you will be able to publish with
Yes.
money and something like that. So they try to push all these open access journal. Even I submitted one journal to SES applied electronic materials, and then they push it to SS Omega. So SS Omega still it's good,
Wow.
but I don't deny that. But still, like they try to push it to open access journal.
Yeah.
So it is the same ways. Like all these publishers are trying to push it open access, and we look at whether we should publish a new journal or not. The same mentality is here also, like whether we should publish in Indian journal or not. And then sometimes what I do is I see, like when I also published SES applied energy materials when it just started, but I thought like, okay, it's a SES journal, let's give it a try. And now this journal is getting popularity, right?
Yeah.
Because it's a SES publication.
Yeah.
And I also see like who all are publishing there, whether there are really big group of publishing there or not. That is the same thing. So in Indian journal, if I see there are papers from reputed institute, reputed what you call scientists, they're publishing in some journals, definitely other people will also be eager to publish there.
Encouraged. Yeah, they will be
Encouraged to
encouraged
publish
to
there.
publish. Yes. Yes, exactly.
Not only way we can think that Indian journal will get popularity, and definitely it has to be like what you call indexed in either Scopus or
Of
whatever.
course.
It
Yes.
will be indexed
Then
properly.
only it will get the popularity.
Web
Yes.
of Science or Scopus
Yeah,
also.
Web of Science or Scopus or Gold Scholar. It has to be indexed somewhere. Otherwise, people will think, oh, it could be predator journal, right? People don't like to publish.
Because nowadays there's a lot in that.
Yeah,
I
that's a
mean,
lot.
and unfortunately, many of them are from India as well. So that's another thing to kind of protect our pristineness, I would say. That yeah, that is one of the challenges as well, I guess, because you always spam them if you'll see such mails, and then
I do get a lot of like, okay, I see your article in this. Do you want to
yes,
publish?
yes.
This is quite common. I
I
mean, we don't
think
want
they're
to go to
making
that.
some software, it seems like. They just pick up some of the article and then just put up those bulk mail to people. Yeah. Uh, Even sometimes I got mail from my co-author addressing to me like, "Dear doctors, my student, and then you have published this and all." So yeah, so that thing, yeah. But nevertheless, I mean, as Manojit said, I think unless the like the prominent groups publish their the other people will not follow that. So that is one of the things that we can do. But yeah,
The point is like we should value our journal. Otherwise,
yes,
outside people they will not value our journal. So that is the point.
exactly.
Right?
Yes, yes, yes. So yeah, I think that's a really good point. So you have any plan in your mind, Dr. Arijit? You were telling me when this thing, or you have
So
any
far, we
knowledge?
haven't any plan, but I think so. You should take an initiative where it will be possible for me.
Okay.
Actually.
Uh-huh.
I'm always thinking like that,
So
but
if you would like to initiate something, please let us know. We can,
yeah,
you can
already
find
I
all
think
of us on board. I can say that. At least me, I'll say that.
our director of our school is there, so I like to request him to tell something in this regard because he has a chance to do take some initiatives. So please share your thoughts in this regard.
I was listening
Thank you, sir.
carefully and amused to some extent because for the last several minutes, what was being discussed basically a chicken and egg problem. whether good work come first or good journals. So that is something I would not mm, touch upon much because there were a bit charged words they were used, such as forcing. Forcing, intellectual community has its acid dangers. So once if we start, if we even in any little way, if something is forced, then maybe down the line we open the gateway to force. You have to do research on this. Academic freedom, which has been, which is in a sense is sacrosanct in the minds of scholars and researchers, that is something, that is one area. But what Dr. Sudip Chakraborty mentioned initially when I entered the discussion about maybe trying to get a consortium or cluster about computing. Dr. Chakraborty, correct me if I'm wrong, you indicated at that, and that I would urge Dr. Arijit Bagh to take that up seriously, and I would do my part and get our Vice Chancellor's advice and how to do that. That would pave the way, I think, for doing good work, being inclusive, and building a community, a network. Gradually, the network effect, as we call, will start kicking in. And about the journals, maybe a different format. That I leave to the creative imagination of all of you, that if one can think of, I won't even use the word journal, because the moment I use a word, we visualize a picture. The format gets, the media is the message, as they say. If I use the word, there would be a picture forming in your mind. I'm not going to use the word, but some sort of a document. It could be a multimedia system, which one can think of. And if there is creativity, if there is originality in thinking of the configuration and the form and format of that forum, the world might take notice. So there are n number of journals, and the interest in the incremental interest in the n plus 1f would be very difficult to generate. Maybe my appeal to the creative mind of yours is think of a format which is different, which could be unique. Certain things are happening little by little. I come from old school, means my major research was done in the 90s and early 2000s. But nowadays, for example, with these, they're very reputed journals, a whole lot of data, such as in Science, Nature, PNAS, whole lot of very thorough appendices are required. That was not mandated when I was publishing. That's a new addition. So maybe in some fashion, one could think of, again, a creative forum for publishing and disseminating, rather. I would use that word, a creative forum of disseminating, stimulating scientific knowledge work in your areas, let us say physico-chemical sciences. It would be something to look forward to. That is my 2 cents worth.
Yeah, I think that is really something worth listening to, Professor Samazdar. So yeah, I think like Proceedings of National Academy of Science, like he mentioned the PNS. I mean, it's really kind of prestigious, but it started with kind of a proceedings of the National Academy of Science there in US. So if something in that direction we can kind of try to evolve, could be something that we can cherish for a long time, probably. Yeah, yeah. So thank you. I think it was really nice input.
Yeah, that kind of
And
Thank you, Professor.
one more thing again, what I find, especially in India and world over, whatever little experience I have, in general, it is said that catch them young. Let us say in football, in hockey, in cricket, in everything, and of course, gymnastics. However, it is my observation that in science, there is hardly any journal, so to say, which addresses the young population. There may be popular science, that's a separate story. You might think of Scientific American could be a bit of an exception, but if we could think of in the chemical sciences directed toward basically the clientele being the youth. Indian youth, you know the demography. There is a large number of youth. And there, the job of or the objective of that forum may not necessarily be to have the finest or the latest cutting edge part, but the developmental aspect of the youth. So that when they join on board, when they get into, let us say, postgraduate, they have some idea. And that's, again, why I'm mentioning it. I'm coming from a bit of a, how to put it, a branding and marketing point of view. Where do you position your forum? In a crowded place where it is saturated, or somewhere where there is a dearth? Something, if we do such brainstorming to identify areas as well as formats which are not crowded, we might come up with an idea which could be eventually implemented to a reasonable amount of success. I'm sorry I interjected it just.
No, no, I think it's really something excellent point actually. Yeah, we can think of because yeah, I mean there's a lot of area which is really crowded. So yeah, I mean the visibility is always an issue for any journal to kind of emerge as a promising journal. So yeah, I think we can always think of that. Maybe we should have some separate session altogether to kind of
Yeah.
stress upon these issues as well. I mean, these are really nice going. I'm really happy the way it's kind of going on. So yeah, I mean, if there is anybody else who'd like to shed light on this particular discussion on the or the whole FTP, it would be nice.
So in this regard, actually, I add one thing. Probably, I don't know whether nationally we can think about some science magazine every year, or maybe like some sort of science blog, where all these review articles sort of like over the field. So the national magazine can have the review of the field in various aspects, and that can come from some reputed institute. Probably that will get popularities fast, and then later on we can definitely diversify this. So in that way, probably we'll showcase like what is nationally going on. Like right now, what I feel is okay, there are so many like thousands of journals and everywhere it is going on. But if I say like what is happening in India, probably nobody would be able to tell exactly what is happening from India, right? So in that sense, if there is some national magazine, is it possible to like launch some sort of national magazine where all these researchers basically uh, submit their review articles in terms of like, so people will not bother submitting review article, I guess, rather than like submitting actual research article. So
Yeah.
that may get the popularities fast. So that's what I can think, that we can break the I mean egg and chicken problem that Professor Samazdar was talking about. So somewhere we can break that. Right? That is
Yes.
what I have one thought in my mind.
Yes,
Like
yes.
maybe the other possibilities also there.
No, I think
So
it's an excellent point, I would say. Yeah. Yeah. Please, Dr.
So
Ghosh.
I think that maybe not considering the national concern, but as far as our university is concerned, as also our department is concerned, so we are really in line. It's in the pipeline of having blog, and maybe it will be our privilege, the happy privilege for invite you all, the speakers present here, and we wish in future many more will be added to them, to write some of your research experiences or some topics in the blog in near future, which we will be going to launch very very soon. And I'll be happy if you contribute to their your thoughts as well, which will be maybe for a token, Dr. Bag said, it's very good thought that it has to be come from the national point of view, and then only we can have our own national things, that we can spread to much more readers, the scientific readers across India, so that can reach much more places what actually going on in Indian perspective. So that's very necessary. So that's what I want to tell. And I think we are very close to the
So there is
valedictory session.
one
Yeah,
hand raised from Dr. Jishnu Chakraborty. Maybe we.
yeah. Is it raised from before, or maybe we can allow him to talk if he has something to say? Yes.
Yes, I think
Yeah.
it would be a good idea to open it up.
So,
Yeah. Dr. Chakraborty, can you hear us?
okay. Yes, I can get it all.
Yeah.
In this gloomy, really, in the context of this poor condition or the gloomy picture of the Indian journals, I like to share some good news. I hope you will be happy to know that probably you know that there is one journal of Indian Chemical Society, CHICS, that is
Yeah.
published by the Indian Chemical Society, that is from Kolkata. Very recently, in the last 1 month, very near, I was attending the conference, international conference, and there Professor G.D. Jadhav, currently the president of the society, he has declared that CHICS is going to be published in actually the Elsevier. So I think the more and more budding scientists will be sending or publishing their articles, their research work in this journal, and to give a revamp of the potentiality that used to be published once upon a time by Professor Acharya Prafullo Chandra Bose. So, not need to lose heart. We must look forward and go ahead. If something is seeding right now, uh, there must be some good future because we have so many technological support around us. So this is the good news that I wanted to share with you.
Thank you.
Yeah.
Thank you. Yep. So maybe Dr. Ghosh, you would like to say something?
Yeah, I think we have discussed quite a lot of things, some scientific points of view, and also some promotional things that need to be done, and that's the urge of the current scenario considering the Indians science progress. So I think our participants, as well as from my own behalf, I have been enriched all 5 day long, and especially in the discussion session, as you have answered my queries as well, and also the queries of the participants as well. So thank you, the panelists, again. And I think we are almost close to the valedictory session. So I will transfer it over to Dr. Chakraborty, being the chairman of the session, discussion session. So just say your
So
concluding
I
remarks on
just,
that. Yes.
yeah, I think I can just wrap the whole things. I think it was a really nice initiative, and I could see the exuberance in the participants, as well as we are also feeling really excited to share our thoughts as well. It was been really nice, and I think this can be a really good starting point. As we mentioned quite a bit of points. One is the forum. We can have a common forum where we can kind of share our ideas, collaboration, and anybody can jump into that to, if according to their own need. And also another thing is the different kind of vacancies, which for the newcomers it would be really nice if any lab they are kind of opening a PhD position or postdoc. I will personally do that. I mean, any kind of interested student can always contact us. And also there could be, if it's possible, I mean, with MAKAUT, if you would like to have some kind of a MOU kind of thing where we can exchange students
Yes.
with IIT Indore, Roorkee, or Bombay, or NIT Sikkim, that could be something also that we can think of, where one or two students of your batch, of your MSc batch, I mean, whom you think kind of has the potential. I mean, they're always welcome to visit our lab and can stay there for a couple of months or maybe more than that. And we try to kind of, I think we try to equip them as much as possible to have some kind of the summer project, like it happens in like different. Also, I think this INSA and this kind of thing. So not only in summer but in any other time also, according to the schedule of the academic, the whole course. So that could be also something like we can always exchange, and that could be another way to, I mean, because students are the instrumental fact. I mean, we can actually explore our different collaborative ventures through them, and that could be another thing. So in my lab, I would say, I mean, anybody from any of you are always welcome. So yeah, I mean, that could be something we can also try to do, so that the thing that we didn't get 10 years back, we can actually give that back. I mean, when we started our PhD, we didn't have that much facility, but at least the students who are right now in their MSc or MTech or even BTech, we can try to do that. So that would be something that we can go for. Yeah. So with that, I think, I mean, it's all from me actually. So
Thank you, Dr. Chakraborty. It's so generous of you, and it will be really a big opportunity for our in-house students if they can grasp that opportunity and get an place in your lab. And also Dr. Datta and I think Dr. Bhattacharya and Dr. Bagh, the panelists we have and the speaker we have, they are eminent in their own right. So if they get the opportunity to get admission for the PhD program or the project work or the summer internship, whatever that can boost up their knowledge in this domain, it will be a privilege for them, I'm sure. So definitely we will convey these things, and I think they are in the participant box as well, so they can hear by themselves as well. So, and they will be happy to grab the opportunity. So thank you very much. Thank you. So I think with this we will conclude the discussion session, and I think now I will request the head of the Department of Applied Science under the School of Natural and Applied Science, MAKAUT, West Bengal, Dr. Radha Vallabh Bhaur, to please conduct the valedictory session. And so far what I have been informed that our Honorable Vice Chancellor sir will be joining us soon. And sir, Dr. Bhaur, over to you, sir.
Dr. Ghosh,
Yeah.
I think we have discussed.
I think yes. Sorry. This is sorry from my behalf, because we not only from the academic point of view, we wanted to have something, some cultural thing, because the researchers or the speakers, they are doing excellent work in their field of research. Not only that, along with that, they are having their passions in some cultural things. So with that, I came to know that Dr. Manojit Bagh, he is very much interested and passionate in the field of music. So may I request Dr. Bagh to please share something with us.
Hello, Dr. Bagh, are you there?
Dr. Bagh, can you hear us?
Please unmute mic, Bagh sir, Manojit Bagh sir.
Microphone is
Dr. Bagh, can you
muted.
hear us?
His microphone is off.
Maybe he's bringing his instrument or something. Let us wait for a second.
Yeah, definitely. It's worth.
Ghosh, you might consider giving him a call if you have.
So I think Dr. Arijit Bag is already having that thing, I guess. Yes.
All
Yes.
right, good, thanks.
Yeah. Yes. Thank you, sir.
Yeah, he's bringing his instrument. So just
So my guess was not wrong, huh?
yeah,
No. Yes, sir.
Okay.
Yes.
While we are on this, can I just ask for something to all of you?
yeah.
Sure, sir. Sure.
What I mean is, I really appreciate the goodwill expressed by all the panelists, summarized succinctly by Dr. Chakraborty. Now, maybe we can consider using online mode, having a systematic lecture session. Say, for example, in your class, if instead of, or in my class, let me put it that way, I teach the students every time they see me. And if it is possible to have a visiting faculty or someone giving one lecture, if one, a different phase, different viewpoint, so such thing could be organized amongst us. Dr. Arijit Bag, Dr. Taposh Ghosh, you spare maybe some time every month
Yes.
and give a lecture. Similarly, other panelists. So every month, if we can think that if there is a course X going on, we schedule it in such a way that every month there would be one guest lecture from using online mode in somewhere around the topic, which is going to enhance the syllabus. I mean, it would be somewhere around, but it does not necessarily have to be right on the dot of the syllabus. So this is my position before the panelists. That way we
Sure.
can keep on our the gel better.
Yeah. Yeah. Yeah, I mean, for me, I'd love to do that. I would love to participate in any such initiative.
Yeah.
Thank you.
Thank you. Okay. I think Dr. Bag is with us. I just saw him. So may I request Dr. Bag to kindly share your other expertise in the field
Begin
of music?
begin his recital, please.
Yeah. Yes, sir.
Okay.
Yes.
Actually, I did not play for a long time actually. So yesterday, actually, my brother called and asked, like, can you
Please open
make?
your video, please.
Yeah, but my mother gun is not here, so maybe I need to bring it. So maybe like, do you want me to play now or like?
Yes, yes, yes. Please, please.
Okay, let me see.
Yeah.
It is.
Dr. Bag, maybe you just unmute yourself, I guess. Dr. Bag, can you hear us?
I think he went to bring his mother probably now.
Okay.
Yes, I guess so. Hmm.
Yeah.
Looking for where I kept it. So
Yeah.
I don't know. I don't know. I'm not in practice for a long time, so
No, it was very nice. Nice to hear that voice tune. Thank you. Thank you very much. I think you managed some time apart from doing some excellent research to pursue your hobby, and it's really nice to see that. Thank you very much. Thank you.
thank you.
Thank you. So I think as we were moving, so we had a very excellent session so far. I enjoyed every bit of that. And may I request Dr. Bhaur, the head of the Department of Applied Sciences, to kindly conduct the valedictory session. Sir, over to you now, sir.
Okay, thank you, Dr. Ghosh, for giving me this opportunity. Now, I have just joined around, say, 15 years back, and I have got a chance to listen to a part of the speech of the panelists, and I have seen that last 5 days, so many things has already happened, and our director also noted all these points that what to be done, and Professor Chakraborty also mentioned and extended his hand, what we can say, for our university students. And I must give him our thanks, sincere thanks, so that we can also be a part of your knowledge transfer process, and our students will get some chance to enrich themselves. And as well as obviously our institute is not up to that level like IITs. So in that respect, we can, if we can enrich ourselves with the facilities which is available in IITs, then it will be very good, not only for our institutes, but also our students and for future program also. So that will help a lot, and thanks all the panelists on behalf of me, on behalf of our university, for giving their giving us this chance to have collaboration and ensuring us for their support. Thank you all. Our vice chancellor is supposed to come and join in this valedictory session. Obviously, last 5 days I could not attend all programs, but attended few of them, and I have seen all the speakers. All the speakers have delivered their speech in such a way so that transfer of knowledge can be maximized, so that their tone and mood and rhythm, all these things are tuned in such a way that their knowledge can be transferred. Maximum or absorption level to the participant is of the better way by which that can be transferred, means hold time and transfer propagation time is maintained properly. That is very important for any teaching, and they have done it very nicely. I am very happy that in some cases I also hurriedly say something, and so that and most of the thing going out from there, not inside entering into the main. So that time is necessary, because hold time and propagation time, that is very important in the case of device as well as in the case of brain also. So they have done it very nicely. I have most of the speaker, whatever I have attended, I am very happy with that, and I am many thanks to them that monitor it properly and done it properly in time maintaining the time sequence. So apart from the all speakers, there are so many other persons are also involved in this program. Now, our vice chancellor is expected to come and join. In the meantime, I can request our director also to Professor Samazdar to give his concluding session. Or one thing we can do, we can request our those who are present at least in this meeting, their opinion about the program, or if they have any suggestion to implement.
I think that is a good idea, sir. Let us open it up to all the panelists.
Yes.
I mean, all the participants
All the,
can get to hear.
For the participants, okay, that will be good. For if we get some here, want to hear from the participants, at least few of them, what is their feedback, what is their opinion regarding this program.
To use a contemporary jargon, we can crowdsource if necessary. Yes, Dr. Ghosh, you were saying something.
Yeah, sir, I was saying that in the beginning of the discussion session, we let the participant with the opportunity to discuss with the panelist and also share their thoughts. So we had some participants already shared their thoughts at that time. So maybe if someone else who want to share their thought, definitely they can come up and raise their hand, and we will allow them to talk, and they can share their thought regarding this 5-day FDP program. And because due to the constraint of the time as well, and so maybe I think we can, until we can have the raised hand from the participants, we can have that at least from our speakers, the eminent speakers. We can have their thoughts regarding this program in future, their thoughts on that. So I think we can have that, sir. So just to say this.
No long case. Is there any?
Okay, I just add one more thing, because I have been involved in a few QIP program.
Okay, thank you.
One, I feel like, okay, slightly different experience for me, like teaching online and giving seminars online. So I have to be part of QIP program for the last 2-3 years now, but they are all like in person. So this is the first time I'm presenting in front of this virtual audience and virtual platform. This is quite exciting, and I myself bit honored that I've been asked to present my work here. So I'll be happy, like in future, if I've been called, then definitely I'll be happy to talk again. Thank you.
Thank you, Professor Bhatt, for giving your opinion regarding this FDP. Now I request Dr. Sumanto Bhattacharya, NIT Sikkim, if he can make some suggestion or advice to improve our program in future. Hello, Professor Bhattacharya.
Dr. Bhattacharya, can you hear us?
Hello, Professor.
I think we have our Vice Chancellor, sir, joined with us.
Okay. Well, Vice Chancellor has joined with us. So, sir, I want to mention that our valedictory session has already started. Okay. So, at the beginning, I request you to deliver your speech, concluding speech in the valedictory session, so that we have completed last 5 days program, and all the speakers completed it in time and in proper sequence. And I think all the participants have benefited a lot from here. And not only that, our panelists also, particularly today's panelists in the end session, with the chairmanship of Sudhi Sakoti, mentioned that they have extended their support in future program also. Future program, not only that, some collaboration, and so that our students can exchange, I mean that they could join in different exchange program also with them, with the different IITs, those who are over here. So we our students must be benefited from their support, and I think in future we will be in this, we will able to enrich ourselves, and our students will get some chance to enrich themselves. So with this, I request our Vice Chancellor, Professor Dr. Vaikod Moitro, to share, if you kindly give your concluding speech on this evening. Sir, please.
Okay. Thank you, Dr. Bhaur. So it's great that you have completed FDP on computational techniques in chemistry and material science successfully. And so I can see that there are more than 40 participants, 45 participants. They successfully completed this faculty development programs. And this initiative, faculty development program initiative, that was basically conceived by us through digital platforms a couple of years before. But afterwards, it was made possible only by sincere involvement of all the faculty members under the leadership of Dr. Somasda, Dr. Bhaur, Dr. Taposh Ghosh, and all others. So this is a great thing, because in near future, in the new normal things, there are two, there are two school of opinions. One is one group is saying that future will be normal again, and one group is saying that future will not be normal. And we have to enter in a world with different norms and practices. Whatever it is, but what we are observing, that everything is happening in digital platforms and digital all these things, digital techniques, that is going to affect tremendously all our existing practices, particularly in material science and chemistry. In our this country, we did not have and so until now we are not having much emphasis on computational parts of these subjects. And traditional subjects, chemistry, material science, and all of the subjects like this, one of the thing is now people are working with big data and a variety of data. This data of different natures, different types, and handling all these things will require a very good understandings of this computational tools and techniques, a solid foundation of mathematics, computational programs that are going to be essential and very, very crucial and critical for all the subjects. Otherwise, you see, in near future, everything will be automated, and as it will be automated, so the experiments and all these things which was done with a small volume of samples manually, that are going to be replaced completely. Maybe mostly as a consequence of robotics, as a consequence of automation. This we have to control all these things through proper computer programming, for generation of data, for analyzing all this data, and for getting meaningful insights of all these things. And then we can have one of the problem of this material science, we have to deal with lots of heterogeneity. This heterogeneous properties, heterogeneous behavior, and that affects this, this performance of this material. And that is true for this all research of material science. When the Challenger exploded years before, that was the problem with the problem with the materials, where there was a stress difference, strain difference, and that created a difference in stress and all these things. Now, because of this handling of these huge numbers of data, huge numbers of these properties simultaneously, that gives more better insights in modeling, in all these non-destructive processes of designing many things, and that are going to be very, very essential in chemistry also. As we have to develop lots of these chemical processes fundamentally based on theoretical principles of chemistry, be it biochemistry, be it chemistry for industrial chemistry, and all other things. There also lots of this heterogeneity is involved. And in country like us, as we have large number of diversity, be it biodiversity, be it this diversity of our systems, our cultures, and all these things. There, the scope of this computational techniques, handling big volume data, mathematical tools and techniques, these are going to be paramount. These are going to be the essential skill for all the future generation researcher, for all future generation academics. Even when we were this researcher, We did all the experiments in our laboratory, maybe in limited volumes, and we published papers and all these things. But most of the cases, whatever it is being observed, that out of our all academic exercises, out of our all academic output, very few are getting translated into proper practicals or commercial endeavor. The reason behind it is, when this is going to be upscaled, this is going to be practically translated in real business scenario, most of the cases we are witnessing failures. Why it is so? Because the thing is, whatever we're reporting, maybe that is true within certain range and certain limits. And this limitless, limitless practices, limitless, system generation, that is possible only when we will be habituated, we will be handling with this huge amount of data, and that are going to be slowly and this steadily penetrating all our academic scenario, academic cultures, even in pharmaceutical practices, in drug manufacturing, in handling this natural products, all these things. People are now giving emphasis on all these tools, techniques, and solid basis on mathematical concepts and skills, and that is going to be one of the important area for successful career also, because most of these multinational organizations, they are trying to identify persons with this tremendous with a good solid understanding of all these the computational techniques, computational tools, informatics, analytics, handling the experience of handling data, good mathematical foundations. They are looking for candidates like this. This is my first-hand experience. I know that many of these multinational organizations, they have taken up this endeavor in that way, and therefore, for irrespective of disciplines, irrespective of branches, it is true, very true for material science and chemistry, but it is true for each and every subject. We need to have a generation, we need to have a learning community who will be going to be very, very proficient in handling all this complexity of all these things by applications of proper scientific tools, techniques, softwares, by mathematical, applying these mathematical concepts, and this cannot be neglected. This even I have seen that even for engineering students and students with backgrounds of science, mathematics in many cases are not given proper this emphasis and importance. But this is that now the era is coming where there is no route of for escape. We have to embrace mathematics as a part of our culture. We have to embrace proper this knowledge of softwares, programming, and all these things, handling data and all this. So therefore these types of programs, faculty development programs, is going to be of immense help for our learning community. And this is one stage. We will have more this faculty development program in these lines with great difficulties, with different levels of this standards and all these things, maybe in near future. And my advice, I always tell it, so from this faculty development program, whatever you have learned for the last 5 days, take a stock of it, make it this compilation of all the knowledges, whatever you have gathered out of it, and then try to upgrade it further, augment it further. I can tell you there are huge numbers of resources available in online platforms. Yesterday, one student was asking me how to sir, I want to have some ideas on data science. So where to enroll? So I advise that Johns Hopkins University, they are offering 10 online courses in data science. So if you can complete all these 10 courses, then you will be considered as an international expert in data science. Because whenever you are taking up some activities at online platforms, all this data and information through analytics is conveyed to all these this organization, and they come to know that these students or these learners is taking up these types of courses from these platforms, and there is always this scope of sharing your certificates, all this through LinkedIn, through your professional these profiles with the greater professional society and professional community. So these are going to be the unprecedented opportunities which was not there even a decade before. Now opportunities enormous. Only we need to have proper mentality that we need to upgrade ourselves on a regular basis. We need to have the skill of this ability of learning, and that is being assessed at each and every aspect. Whenever your performance will be assessed, then the primary skill will be whether you have right learning ability, aptitude or not. And if you have right aptitude and ability, then always you will be you can be considered as a successful candidate for any endeavors. So this is my advice to all the participants. Try to upgrade yourselves and have gather more knowledge and information in this area. And whenever we will be organizing similar programs, again join here. Try for this validating or brushing up or your knowledge, for validating your knowledge, or this getting more relevant information, or sharing your ideas and opinions. Here also you can also share whatever you have learned. If something is something more is known to you, or something extra additional is known to you, convey to other learning community, because we have created this a portal through which you can always share your opinion to other learners. This is one of the way for building up knowledge further, because not only we have to act as consumer of knowledge, we have to generate knowledge also, which is called prosumer of knowledge. And that is possible only if we take sincere interest and active interest in all these learning programs. I believe that all of the participants will follow this, and we will have a large number of experts available in near future for handling all these challenging scenario in our real life. And I wish to congratulate organizer further for taking up this endeavor, and my sincerest thanks to the resource persons who have taken up this time for sharing their knowledges and experiences with our learning communities. Thank you all.
Thank you, sir, for giving me advice and direction of coming age education, and for holistic nature of education. It is needed, obviously, because we have to go up ourselves. And for the participants also, they should go forward like this way, so that they can enrich themselves, and a potential, they may be potential to the industry also. Now I request our director to give his concluding remark. Professor Samazdar, Professor Sukendu Samazdar.
Thank you, Professor Bhor. After 5 days of deliberation, there is little left to mention, but to express my sense of fulfillment and gratitude and excitement at the concluding session of this FDP program. I have received independent feedbacks from several of the participants, which motivated me, which have made us feel that this is an exercise which was worth taking up. The organizers, as well as our session conductors, the experts, they know one thing, that the short time frame within which it was brought into fruition. And that is, I particularly express the teamwork, including the resource persons particularly, and all across the School of Natural, Applied and Social Sciences, as well as the university, that something of such quality, and I am kind of allowing myself to use that term because I think the exercise and the FDP has met a reasonable standard of quality, so that all the organizers literally gave their best, supported by the resource persons and the participants. They asked questions, they showed interest, and we are going to continue the network that took shape through this event. Dr. Sudip Chakraborty, he explicitly mentioned the possibility of putting together some sort of a computational cluster. We discussed the possibility of exchanging students and scholars and researchers. We are going to lend our services in a sense of giving visiting lectures to the different institutes, as well as people from the faculty members from different institutes will also give visiting lectures, hopefully once a month in our university classes as well. So as a takeaway, that is not a small platter. So I think I I am going to, through the end of this program with a sense of fulfillment, thanks to the engagement of all. Thank you very much. Namaskar.
Thank you. Thank you, Director Sir, Professor Sukendu Samasdar, for giving his concluding remark. He already mentioned that this program is very, very successful, and it is true. Already Vice Chancellor also mentioned it is possible to organize it within this very short time, means within 10 days, because of the online platform. Because in the offline platform, at least 2 months time is necessary to organize the whole program in the offline mode, in the campus or whatever the place. And at the same time, it is also important that their number restrictions is very limited because of the depends on the so many other factors. So that restriction was not there. So that is one of the several benefits what we have got due to online platform. And our speakers also, within very short time, in some cases, all the time they are busy in moving here and there. They are engaged in so many programs, but now all of them are available in the room, in their home. But obviously, they also have other programs. But anyhow, they can be managed. They can manage it. So that is possible to get a slot in between time. So that way they have managed and given their time. So in that way, it is possible only due to our director rightly pointed out that it is possible only due to digital mode. It is done it in digital mode. So thank you, our director, for giving his concluding remark. And now I think we are at the end. So I want to give only some say concluding some thanks because of that is our gratitude to all the parts of the organizing team. First of all, we must give our thanks to our Vice Chancellor, Professor Dr. Soikat Mitra, because all the time he is encouraging us for motivating us for different programs or go ahead in different directions in such a way that our institutes and our students can benefit from different ways, and so that they can update themselves, because update is very necessary nowadays because of the fact without any update we'll become backward in the backside, and it is very difficult to survive. At least for survival, at least we want to go up and for that different types of program is to be developed, and our Vice Chancellor is always encouraging us to do such a to progress it. So thanks our Vice Chancellor, Professor Mohito, for giving sincere encouragement to us. And next, I want to give my thanks to the Vice Chancellor, Islamic University of Science and Technology, Jammu and Kashmir, for their collaboration, because they have collaborated this program along with the TECPIP, along with our university. They are also participated and collaborated. So thanks to him for on behalf of the organizer. And obviously, I must give my thanks to the TECPIP because they have given the total fund, and for their fund it was possible and to organize this program. So thanks to the organizing team of team members of the TECPIP. And I also give my thanks to all speakers, because within I have already mentioned, and I want to mention that they have given their time within very short time, which was very difficult to other moment, because in online it was possible because of the online, all of them are available in their home, and so that they can able to give their slot within the short video of time. So thanks to all of them for participation, for timely entering and finishing their job and interacted with the students and enriched our participants and enriched our own, enriched our all participants and our faculty members also. So thanks to all of them. What I am telling. And again, I want to thanks to our webinar team, and because of the without their help, it was not possible to organize it because they are not getting time because throughout the day something is happening, and they are busy from very morning to end of the night. So they are really working hard, and so we must give my sincere thanks to them. And our another part is the participants. Without their joining, it was not possible to organize it without their interest. And we are very happy that they are also interacted, shows their interest, and they enrich themselves from their feedback. We have already got some idea. So that is the main force behind us, because they have enriched themselves. If we understand that they have enriched themselves, then that is the input what we have got from them, and that encourages us to organize such programs so that participants can benefit from our program and they enrich themselves. They can do something after returning to their own institute, and our purpose is served. So not that we are happy with the serving this one, but obviously we have to do it in future with some more additional things which can help us to with in future, depending on the future requirement. So that is to be updated ourselves, and accordingly we have to organize that type of program in future also.
Professor Bhaur, if I may, since you indicated about the future, there is one coming up from 2nd through 6th of November on the art and craft of writing, scientific and technical writing. So there is going to be an online faculty workshop, which is going to be open to essentially the knowledge community, the researchers, the PG students, as well as the faculty members. I just thought I take this opportunity. So I beg your pardon for interrupting, Professor Bhaur.
Okay. Thank you, sir, for giving this input to the participants, so that they can, if they interest, they can also participate in that program also. And they can communicate it to their our own students or own friends, so that they can also participate in the program, in our program. And from these inputs, they can get some idea that what are the level or way by which we are presenting, or our eminent speakers are presenting. From that, they can get some interest and they can participate. So thank you. And lastly, I want to give my sincere thanks to all panelists and all the members of my department, of my school, because all of them have participated in the program, and all their effort we have assembled. They may be in the back scene, they may not be seen in the front side, but they have also supported us to organize it. So thanks to all of them. And I am very happy that we are also very happy from the different feedbacks and your opinions that that this program is to some extent at least successful, and ultimately we have reached the goal. Successful program is the ultimate goal of the organizer, and in that way we are successful. And with this and giving thank you all, I am closing my speech, and I request Dr. Ghosh to take over the session.
Thank you, Dr. Bhaur, for presiding the valedictory session. And I think most of the things have been said. And I would like to thank the panelists again. And also, I would like to thank our Honorable Vice Chancellor, sir, for taking your time to deliver your valuable speech in the valedictory session. Thank you, sir. And it's been your encouragement, the constant encouragement and the motivation that helps us to assemble all the things and to give us courage to organize an FDP program in that short span of time. Is without your blessings and encouragement, it would not have been possible. So thank you, sir. I would also like to thank, being the convener of the FDP, our director of our school, Professor Shukhendu Samazdar, for guiding us all through. It may be late night, it may be early morning, whenever we contacted him, I mean, because of the foolishness of us, maybe irrespective of the time, he has responded whenever we contacted and guided us all through how to put up the things, and it's all the benefit for the participant as much as that they can get. So thank you, sir, for your guidance as well. I would like to thank the head of the department, Dr. Bhaur, for being there and also helping us with the formulation of the things to make things easy, and also helping the same things as well. It doesn't make sense to repeat all these things because it's a team effort, and you all have been so generous to help us to get these things. And I must thank very much Dr. Arijit Bagh, without whose effort it would not have been possible, really, literally, who spent enormous amount of time interacting with the speakers and taking consent of them, and I mean, gathering things to put up the abstract book. So, and so very many things. I cannot mention all the things. There may be a list of uncountable list that we have to go through for last few days. So better not to mention all those, but sincerest thanks to Dr. Bagh for helping me and working as a team. We tried our best, and the response from the participant will show how much we have been successful, and also they will guide us what are the things that we need to uplift in our effort for our future endeavors to do such programs. And also I would like to thank all the members of the organizing committee from the Department of Applied Sciences and also from the Department of Material Science and Technology for lending their helping hands whenever needed. And especially to mention Dr. Anirban Roy, Dr. Monalisa Char, Dr. KP Das, who have been so generous for taking their time and helping us. And definitely the major part was the panelists, the speakers, who have been so quick responsive. I must say that they have prepared their sessions very quickly, and to mention Dr. Sudip Chakraborty, Dr. Manojit Bagh, Dr. Sumandra Bhattacharya, Dr. Achinto Kumar Datta, Dr. Ayan Datta, and so they all have been so generous, and thank you all again. And we definitely look to collaborate in so very many aspects with all of you, and so that our students and on our personal behalf we can get enriched in terms of knowledge and in terms of scientific aspects. And so thank you very much again. And also I'd like to thank our participants for being there all through the 5 day. It's 4 hours every day, not something that very easy because of the data consumption. As we all know, in today's time when we cannot go out, it necessary for your relaxation, for your recreation as well. But you took your time, all the participants, they took their time to keep their data available for joining this FDP program 4 hours a day. So thank you again all, and we have some very good interactive sessions. So, and also just one last announcement maybe for the participant, that the link for the quiz and the feedback form has been provided in the chat box. So just go through that one, fill out the feedback form and the quiz. This is mandatory to get the certification, so kindly take care of that one and submit your response whenever, as early as possible, and whenever it's stated. So thank you all. In any case you need anything or any information, feel free to contact us. You have the WhatsApp group, you have our contact details, so we'll be happy uh, to provide you with any information you need. And one more thing to announce regarding the certification thing, that it will be provided in a couple of days time, because we are having so very many FDP programs in MAKAUT currently. So the technical team will need some time to prepare the certificates, and definitely when it prepared within maybe, I hopefully it will be within 2 or 3 days time, we will be sending you via the email. So thank you again, thank you all Thank you for your time, and also I would like to thank Prem Kumar and his team for the relentless effort they have given, and whenever we wanted to come up them with something, they have responded, and without them it would not have been possible at all. So thank you, Prem Kumar and your team. Thank you again. Thank you all.
I am leaving. I am leaving, Dr. Ghosh.
Yeah,
Sir,
thank you, sir. Thank you for taking your time. Thank you, sir.
sir, the link has been given in the chat box, and
Yes,
sir,
yes.
the quiz will be open till 10 p.m. tonight because there are questions for the quiz.
Okay, so
Uh,
just maybe in the chat
so,
box you can type that as well. So just let the participant know that it will be open until 10 p.m. Maybe it can help them. Otherwise, maybe tomorrow morning they try and they couldn't submit that. So just if you can help me with that thing. Maybe in the WhatsApp group we can also post that thing, that the link and the deadline for submitting the feedback form. That can help them.
yes, sir, yes. So,
Yeah.
sir, so if you give the permission, we close the session, sir.
Yeah, I think I'm not sure VC sir is still here or not, but it's showing that he's still here. So maybe with his due permission, sir, can you hear us? Are you here with us, sir?
I think sir is busy in some other work.
Okay,
Engaged
so
with some other
I think we need to wait until we get consent from him because he is still in the panel. So
yes.
maybe we need to wait until he responds. I think yeah, sir has left. I guess yes. Yes.
Yes.
So Dr. Bhattacharya is here, but I think we can